Yeah, okay. Arun, I have made you the host. Yeah.
Good morning, sir.
Good afternoon. Good morning.
Yeah. We are just separated by 2.5 hours.
Yeah.
How are you, sir?
Yeah, I'm good. How are you?
I'm good, sir. Very good. Thank you. Yeah.
Okay. So is the campus open now?
Yeah, campus is completely open, sir. It's been so last 8 months we have been working. PhD students are allowed to stay on campus and working. Only the coursework like BTech, MTech first years, the online is going on. And from January 1st, we are we are open to offline classes.
Okay. thanks for joining and
Of course,
for
sir. I mean, it's an honor for me. I feel so privileged. It reminds me of like a few years ago. I
yes,
used
yes.
to present and thanks to Varun Bhai.
Thank you, Chandra. Thank you very much for accepting this and taking this honor. Thanks a lot.
It reminded that I also got
Yeah.
1 hour.
8 years ago, you were the winner, right?
Yeah, in 2013, I got this award.
Yeah.
Thank you. Thank you.
So it's good to see that the symposium also has like come so far, right? Now it's 11 years.
Yeah, it has been, I mean, I remember in 2011, it was with 3 participants. Very few participants were there. After that, I think in 11, I think so many are there.
Yeah. I mean, one particular year, maybe not many. But
yeah. After that, it went like anything. And it used to be only 1 day symposium. Now, I think it has gone to 2 days. It's really going well. Of course, I mean, the spintronic community is increasing in Singapore as well. Yeah. It's growing. That's the reason.
So you have the program with you, right?
Yeah, I have, and also Warren has shared with how to mark and everything. So I'm ready with everything. Yeah.
Yeah. Okay.
Yeah. Thank you.
Senkai is supposed to come with it. Varun?
Yeah, he is, but I'm seeing him whether he joined already. He has not joined yet. We still have 2 minutes, but I hope.
So he has the link, right?
Yeah.
Zoom link? Okay.
Yes.
Okay, Senkai is here.
Yeah, so we can get started.
Yeah, we can start.
Yeah, so welcome back everyone to the second session of this Magnetic Symposium 2021. So this session will be chaired by Dr. Chandrasekhar. He's an assistant professor in Indian Institute of Technology, Hyderabad. He did his PhD from here and TU from SPMS, and he joined there around 1.5 years back, IIT Hyderabad. So he will be chair in this session. Welcome, Chandrasekhar. Please take the mic.
Thank you. Thank you so much. Yeah. So should I ask students to start presentations?
Yes, you can ask. Yeah.
Yes. So yeah, thanks a lot. First of all, it's an honor to be here. Where I was just to tell the students, others may know it. I mean, I participated in 3 of these presentations from 2011 to 2013, and fortunately, I won the Best Presenter Award in 2013 also. So I feel so privileged to be here today. So I request Mr. Heng to start his presentation.
I am here. Okay. But can I share the screen because the host disabled the screen?
Yeah, please go ahead.
No, the host has disabled participant sharing the screen.
Yes.
Yeah.
Give me a moment. I still can't share the screen though.
And now you can.
Ah, okay.
So, Dr. Warren, I think I believe that he has 10 minutes to present, right?
Yep.
So, around 10 minutes, I will give you a.
Okay, so I'll start now, sir.
Yeah, please go ahead. Thank you.
Good afternoon, everyone. My name is Yuanxiang, coming from the Spintronics and Magnetic Material Laboratory of the NUS of Singapore. Today, I'm actually excited to share a proof of concept, the electrical detection of ferromagnetic resonance in bulk YG sample covered with a layer of silver paint. This project is possible under my guidance of, or under the strong guidance of my supervisor, Professor Mahindran, the gentleman on the bottom left. So before I carry on, maybe let me share with you about some ideas of YIG. YIG has altogether 5 Fe3 plus ion in the single unit, and out of these 5, 2 of them are actually in octahedral structure, and 3 of them are actually in the tetrahedral. However, these 2 are actually having different spin, and hence they will couple anti-ferromagnetically through super exchange. This gives rise to the reason why YIG is actually a ferromagnetic material at room temperature. Metal transport in the ferromagnetic heavy metal bilayer thin film has actually attracted much attention, especially in the area of pure spin seeback effect, spin pumping, spin Hall metal resistance, long spin coherent lengths. And the reason why this is possible is because the platinum is able to convert thermal and spin current in YIG into measurable voltage through the use of inverse spin Hall, owing to its strong spin orbit interactions. While preparing for this project itself, I actually chanced upon many groups that actually researching on the YIG platinum layers, especially let's talk about the top left-hand corner. By this group, they actually did the YIG platinum in CPW, measuring the VNA S11 parameters to investigate on the frequency dependence of the spin current emissions. Bottom left-hand side itself, another group that actually did the similar setup itself, but in this case, they measured the thin film and the single crystal, and their conclusion was spin Hall metal impedance is frequency independent up to 3 gigahertz. Top right by JCS Santos, in this case itself, they actually investigate on the effects of different capping layer, namely the silver and the silver and tungstens on the YIG thin film, and the effect it has on the Gilbert damping parameters. Somewhere near us in the NTU NIE, led by Dr. Rohit itself, they actually investigate on the magnetic field dependence electrical impedance using a copper strip coil. And this gives us some excitement because today we are actually here to share the proof of concept. That means we were wondering whether we can actually electrically detect the ferromagnetic resonance in polycrystalline YIG sample without the fabrications of any CPWs. And in this case, before I carry on sharing my experiment data, maybe let me share with you the preparation process that we have. We purchased the polycrystalline powder from a commercial source, Sigma Outreach Singapore. Upon reaching us, I actually pelletized the sample and annealed it at 900 degrees Celsius for 12 hours. After which I actually got a rectangular block of dimension 6 by 4 by 0.7 millimeter to do 2 measurements. One, the magnetic measurements at room temperature, the other magnetic impedance. So in this case, let me share on the on the right hand side of this screen, the magnetization curve. As we can see, this is done at room temperature for VSM Lakeshore. As we increase from low field to high field itself, we see a sharp increase in the magnetization, and it saturates up to about 1.47 mB per formula unit. And in this case, the coercivity, quite small from this screen, is about 20.7 oisted respectively. This curve we would like to conclude here is it actually shows the ferromagnetic characteristics of the YIG at room temperature. After these measurements, and we are assured that this is actually the ferromagnetic material, we actually bring over to the magnetic impedance measurement. How do we do the connections? Allow me to share, maybe in this case, so we start from the bottom left. So the one I circled using my mouse click in this case, we can see that there's this machine, the E4991A single port impedance analyzer. That is where we do our measurements with. So the sample, the similar rectangular block that I did for VSM measurements, is being now mounted onto the sample probe on the top left using the silver paint. So I paint both sides, both ends and at the top. The purpose of doing this is because when we connect this to the measurement setups itself, it allows the MW current to flow along the silver surface from the ground back to the from the signal line back to the ground. Throughout the whole entire measurements, we assured that okay, the electromagnet and the transverse magnetic field that's being provided by the MW current is always perpendicular to each other, which is a favorable configurations of FMR setup. The frequency range we actually measure is 900 megahertz to 3 gigahertz of 0.1 gigahertz interval with very low power to avoid any heating. The R and X are measured simultaneously, from which we extract the data to manipulate into MR and MX for calculations, as what we shown in the formula bottom right. Allow me to show the data at 1 and 3 gigahertz of the left-hand panel. At 1 gigahertz, as we move from high field to zero, that means positive 5.2 to zero field itself, we can see that the resistance, blue ink, is actually showing a rapid increase in the peak itself at about 40 oyster. I'll call it the critical field for 1 gigahertz first. At a similar critical field value, we can see that the reactance shows a sharp peak followed by a rapid dip at the same values. Similar features are actually being seen at the 3 gigahertz itself. However, you see that there's a peak, rapid peak and dip. It happens at a slightly higher field value of 1.26 kilooyster. We also try to plot into the MR and MX in blue, the MR, green, MX right-hand panel. So what we see here is, if you see the dark shades of blue and green, these are actually where the peaks are occurring. We can see that as you move to the higher frequency, the peaks actually shift to the higher field values. One thing we'd like to highlight here is at 1 gigahertz itself, the MR value is approximately just 4%, but when you reach to 3 gigahertz itself, the MR actually shot to about 2,440%. So from this experiment, we conclude that in this case, because YIG has very high resistance at room temperature, then about 12 ohms, so we can conclude that in this case, the current that flows through is only through the silver. So the silver, when the current flows through the silver, it creates the oyster field, which is transverse to the, which is transverse in the direction, and it always interacts the magnetization of the YIG. The impedance that we measure from the experiment is actually affected by the dynamic magnetization of the dynamic magnetization process of YIG, namely MR, which is directly related to the chi double prime, and MX, which is directly related to the chi single prime. So as we recognize the fact that the R and X itself resembles the absorption and dispersion field curve, which is directly proportional to chi double prime, as what we said just now, the out of phase and chi single prime in phase respectively, we try to fit the MR graph into the Lorentzian fitting functions, which accounts for both the symmetrical absorption and disymmetrical, the dispersive nature. So shown on the left-hand panel itself, we only show 5 frequency, namely 1 to 3 in multiples of 0.5 gigahertz. We can see that the curve fits very nicely. So from the Lorentzian fitting function in the green color box bottom left, we actually extract 2 different parameters, namely the HR critical field and the delta H itself, the line width. So using the HR values itself, we plot a graph of frequency versus the HR critical field regions, which is on the right-hand side, and we fit it into the Kita expression for the in-plane ferromagnetic resonance equations, as what we've shown on the bottom right. So from here, what we can conclude is we actually have 3 parameters, namely the gamma by 2 pi, 4 pi M effective, HK. When we are done with this polycrystalline sample, we were wondering if we were supposed to do it for thin film, that means YIG thin film, how would the result be and how does it differ from our polycrystalline sample? This is where we actually, we need to first express our great thanks to Dr. Rohit from the NTU NIE for allowing us to use the 45 nanometer YIG thin film that they have used in their previous experiment also. But this time around for my case of study, I actually put the thin film onto the same MI probe sample, but in this case, covering the silver pane on the top and the side. So showing on the right-hand panel itself is actually, again, the MI experiment, the magnetoresistance data. We can see that the symmetrical peak about the zero field is still there for all the frequencies. And in fact, if we increase the frequency, the peak actually shifts to the higher field value, which is in accordance to what we see in the ceramic samples that I extracted a while ago. Likewise, if I look at the contour plot, the top right-hand corner, we can see that, oh, the dark shades itself indeed shows the shift. And from there, we extract using the Lorentzian fitting function, the critical field values. We can see that this bottom right-hand panel, again, we fit into the Kita relations. It gave us 3 important parameters that we're trying to compare. Gamma by 2 pi, which is 2.789. This is actually very closely related to the literature reported value of 2.8 megahertz per oyster. The one that I'm very keen to share is the 4 pi M effective and the HK, because through the thin film itself, the 4 pi M effective is about 1,185, which is very close to what we get from our polycrystalline sample, 1,111. Likewise, the HK is actually very close to what we have reported in our ceramic sample, the 67.6. So this is where the excitement came from us, because we were sharing the proof of concept of using silver paint to detect the FMR signal. And it seems like this method actually works. We didn't stop there, of course. We moved on to look at the Gilbert damping parameters of both samples. So on the left-hand side itself is where it's the thin film covered with silver paint. We see that alpha is actually very small. It's about 1 times 10 to the power minus 3. However, for the bulk sample itself is slightly bigger, but as we were trying to prepare for this report itself, we actually compared with one of the available literature value from JCS Santos. His YIG capped with silver metal itself, the alpha damping parameters itself, the Gilbert damping parameter itself is about 0.017, which is quite closely related to our 0.019. Hence, in this case, we would like to conclude that in our investigation, the high-frequency metal transport in insulating bulk polycrystalline YG sample was investigated just with using the silver paint on sample, and it's measuring the magnetoimpedance in the frequency range of 1 to 3 gigahertz. The MR shows a sharp peak, and the MX shows a deep peak in the critical field regions, and it shifts to the higher field with increasing frequency. One thing we would like to highlight here is it actually follows the Kittel relation for the in-field FMR. Hence, we would like to conclude that the magnetoimpedance can actually be a quick plenary ferromagnetic resonance characterizing tool for newly prepared bulk polycrystalline sample, which is one of the important steps prior to the fabrications of thin film. With that, I come to the end of my presentation sharing. Thank you so much.
Yeah, thank you. You're quite in time. Okay, now the talk is open for question and answers. Anyone from the audience would like to go first?
Please raise your hand, and then you will be asked to open the mic.
Okay, so let me go first in that case. So, Mr. Lee, could you please go to fourth slide?
This slide.
Yeah. Just from the MH curve, how do you conclude that this is a ferromagnetic material? You mentioned
actually,
that.
okay, initially, I didn't really conclude as ferromagnetic material. It is just that usually a typical magnetization curve to my level of knowledge or understanding, we can actually conclude either it's paramagnetic or ferromagnetic. So in my initial conclusion was actually it was ferromagnetic. But upon careful discussion with my supervisor told me that actually YIG is ferromagnetic at room temperature. So he actually suggested that why not I just look at a few literature readings. So while we were preparing a similar manuscript for submission, the editor also highlighted the fact that we should actually highlight that this is actually a ferromagnetic sample instead of ferromagnetic, though the data samples is the same. So it's because of the structure, yes.
Okay, so let me ask a fundamental question. Okay. So if at all I give you a sample and I didn't tell you that whether it is a ferromagnetic or ferrimagnetic, what kind of an experiment would you do that to prove that, to kind of distinguish between ferromagnetic and ferrimagnetic material?
To my knowledge, when I have to distinguish between ferromagnetic and ferrimagnetic, what I will do here is I'll actually do these magnetizations with temperature, that means the MT curve. Because if it's ferromagnetic, if it's ferrimagnetic itself at a critical new temperature, you will see that the reading, the magnetization value actually starts to decline. That's what I understood. But
the similar effect you will see after Curie temperature, right? For ferromagnetic material. So how do you still differentiate it?
Okay, this one I'm unsure of. Actually.
No, you just think about it because not to put you down or anything. You just said that your supervisor told you that it is ferrimagnetic, you believed it, but being a researcher, we just don't believe. We do an experiment, right? So
yes, that's why if you ask me, the only experiment that I'll actually attempt to do is actually the MT curve. I mean, that's what I remember.
Yeah, just think about it. Okay. Okay. In fifth slide, you said that the setup is made in such a way. Fifth slide, next slide. You said that the setup is favorable for the ferromagnetic resonance. Why would you say that? What do you think that the setup, the configuration is favorable for ferromagnetic resonance?
According to what I was reading while I was preparing for, that means my theoretical reading, background reading, most of the setup that is used to study the FMR itself is usually done whereby the AC magnetic field and the DC field is perpendicular to each other.
Why so?
So that's why so? Okay, this one I need to read a bit further because when I was reading it itself, most of the papers I was reading on actually highlight that it's actually these configurations only.
Yeah, actually the torque is going to be the maximum In that configuration, torque is going to be the maximum. Anyway,
yes, okay.
I would like to ask if, any of the audience participants would like to ask any questions.
Yeah, I have one question.
Yeah, please go ahead.
Yeah. So what's the application for such a high frequency? Do you have something in mind where we can use it, the material?
For high frequency material, in this case, high frequency material, because sorry, you're saying?
Yeah, most of the means your measurements have been done in gigahertz, right? So
yes.
What's the application you have in mind that where we can use this material?
I was thinking more of in the area of sensor, but to me, I'm still having a very big ideas on the sensor part itself.
Okay.
So roughly we have 15 minutes. So
we have to move on.
I think we should limit to.
I'm sorry for that. We'll go for the next candidate. Thank you, Lee.
Thank you so much.
Stop sharing?
Yes.
We have to move on. I would request Shakti Prasad Padi to start your presentation.
Yeah, sure. I'll share my screen.
Thank
you. I've been disabled to screen share.
Dr. Varun, could you please? Mr. Prasad, can you share?
No, it's still showing host disabled participant screen sharing.
Can share now?
Yeah, I can share now. Yeah.
Please go ahead. So you have 10 minutes.
Yeah.
So
are the slides visible?
I'll ask you to stop presentation. Go ahead.
Yeah, okay. So today I'll be talking about machine learning guided development of iron cobalt nickel based magnetic alloy with improved magnetic and improved mechanical and electrical properties. So the overall research topic can be said as accelerated magnetic materials development. So this whole accelerated magnetic materials development can be divided into three important factors. First one is artificial intelligence or ML based. The second is rapid synthesis, and third is rapid characterization. Now, rapid synthesis and characterization together, it's called as high throughput experimental methodology. Now, the applications of the magnetic materials developed by this methodology can be divided into four main categories. One is electrical machines, then data storage devices, third magnetic coupled devices, and fourth are the other applications. To give you some examples, for electrical machines, we have transformers, electric motors, inductors. For data storage devices, we have heat-assisted magnetic recording, magneto-assistive random access memory application. Then for magnetic coupled devices, we have hysteresis, power clutch, and brakes. And other applications, there are magnetic sensors, hysteresis motors, and magnetic actuators. Now, in all of these applications, if we look at the current demand, there's a demand of developing next generation technologies. What does it mean is basically to operate these devices at high frequencies or high operating temperatures or at higher efficiency. Now, for these, there's a requirement to develop new superior magnetic materials, hence the methodology of accelerated magnetic materials development. So what is the problem that we are trying to tackle? If we look at the traditional approach of developing a material, so the first thing what we do is experimental let me on the laser pointer, sorry. Yeah, so we do the normal lab experiments, then we do some theoretical calculations, and also we perform some simulations, and combining all of these, we develop a new material. Right. So this process usually takes around roughly 20 years to develop a new material. A big disadvantage of this process, if we see, for example, in case of soft magnetic alloys for electrical machine applications, is there is no balance of various properties which are required for most of the applications, especially in high frequency ranges. right? For example, if we take iron cobalt alloys in here, it says that for high frequency losses, it's not ideal because of low electrical resistivity, but it gives us high saturation magnetization and high Curie temperature, which might be actually suitable for high frequency applications. But due to resistivity is not very suitable. Now, if we come to the ferrites, for example, it says that it's very good because of high electrical resistivity, but the drawback is it has low saturation magnetization and the mechanical properties are not good. So it might not be able to bear the stress developed in the system when it's put into high frequency applications. So what's the solution, right? Here comes in the accelerated approach of developing the materials. Right. So if we see in here, we take the data what is being developed previously using the traditional methodology. Then we use the accelerated methodology, experimental methodology to generate new set of data. We data fuse all of these and then put into machine learning algorithm. Right. After that, once we develop the model, is basically we have to apply the inverse design methodology, wherein we have to go from properties, target of the property values to predict composition, right? So basically we are going inverse. The model is from composition and processing conditions to properties. So the steps which is involved is basically what we do is we do the optimizations by providing the target values for the properties. And then once we get the predicted composition and processing conditions, we experimentally validate those. Now, if after performing the experiment, if the property values as predicted is not within by experimentally determining is not within the 5% confidence interval, then what we do is we put back the data into the database and then run into the same loop. Now, if the by experimental validation, if we get the values within the 5% confidence interval of the predicted values, then we can say that yes, we have come to a new material. What are the advantages of this is we have fast methodology. Basically, it will take, once the model and everything is properly developed, it will take less than 2 years to actually develop a new material. The second advantage is we can explore a vast composition and processing condition space. And the third, which is important, is we can have optimal combination of properties. So using this method, we can actually develop a new superior magnetic material in a faster way. So how did I go about? So what I did is I collected the data from the literary sources as shown over here. Then I screened the data for relevant and for the relevant information and from reputed sources or good sources. Then finally, we had a data of 1062 data entries of iron cobalt nickel based alloy system with composition and processing conditions. And for the properties, we had magnetic, mechanical, and electrical properties. Then for the data extraction, it was done from text tables and graphs. There were some graphical images which we were not able to extract the data directly. So what we have to do is we have to digitize those. So this step was done using digitization softwares. Then the consistency of the units were maintained, and finally these properties, which is coercivity, Curie temperature, tensile strength, and electrical resistivity were converted into log 10 values. Finally, once we have done the data cleaning and extraction, we'll have a pre-processed database which can be now used for predictions. So as I said, this data was collected from the literary sources, so it has a lot of heterogeneity in it. So basically, it means that from one source we get the mechanical properties, but from the other source we get the magnetic properties. It for many of the materials we don't have all the like both mechanical, magnetic, and also the electrical together. Right? We have very few sources for that. So there was a very much huge missing data inside the database. Right. So in order to tackle that problem, strategy was developed. So for all the properties from composition to proper data, regressor models were developed. And then the model with high R-square and low mean squared error was used to impute the predicted data. Then for tensile strength, specific additional strategy step was used. So we had yield strength and hardness values. Using these values, we can actually impute predicted data for tensile strength for the respective yield strength and hardness values. So once the regressor model was developed, the best model was from the best model was chosen from the set of regressor models, and then the imputation was done by the predictions. So after the imputation strategy, we have the fully filled database. So herein, it shows the heat maps of various regressors which has been used. So if we see R square, we require what do we require is basically high R square, which is basically high accuracy, and low MSE, right? So the error would be less in predictions. So basically, the more red, the more high, the best is the R square. Then the more blue it is, the best is the more blue, which is basically lower side, which is lower side values of MSE, which is better. So accordingly, the best model, once the best model was chosen for the imputation. Now, after the imputation is done, we move on to the inverse design of the iron cobalt nickel based alloy. Right. So for that, what we require first is to develop the multi-property model. For that, the random forest machine learning model was used with optimized hyperparameters. And
sure.
this
be quick to summary. Yeah. Thank you.
Okay. Yeah. So these are the results. So if we see, as I mentioned already, the R square should be high and MSC should be low. So if we see all of these
go
models,
to summary slide and conclude.
Okay. So to conclude, basically we had 1062 data entries of database. Then we had raw database, which is pre-processed, imputed, and random forest model was developed with Bayesian followed by Bayesian optimization, and inverse design was done. Variation of multiple weights in the objective function was also explored to design the application for various applications. And then finally promising composition was predicted, which is iron 64.7, cobalt 14.1, and nickel 22.3. To remove the heterogeneity in the data, high throughput experimental methodology was used, which is basically high throughput flow synthesis, and followed by compositionally graded SPS in order to make bulk samples, and further the properties were characterized rapidly. Okay.
Yeah, thank you, Prasad. Interesting talk. Yes, Vijay Kumar Verma, please go ahead.
Yeah, hi Shakti. Very good presentation. So what was the outcome of your finding? Like you develop a model,
yeah,
and then what it is useful for?
So this model can be used for various applications because depending upon the applications, we can see that by changing the weights of a particular property, we can say that we want high tensile strength and moderately, let's say moderate saturation magnetization. Then we can set the weights for that, and accordingly we can develop a material. For example, in this case, iron 83, 84, and cobalt 16. This would be very good for such applications, right? So basically this is the strength of the model which was developed. Yeah.
And how?
I think let's move to the next speaker. Yeah, it's time over. Probably.
Okay, thank you. Thank you, Prashad. Yeah, we'll have to move on. So I request Hing to start his presentation. Prashad, could you kindly stop presenting?
Okay, sure. Let me share my screen.
Yeah, go ahead, Hing.
Can you guys see my screen?
Yes, I can see. So you have 10 minutes for your presentation. Go ahead.
Okay, sure. Good afternoon, ladies and gentlemen. My name is Hanin, a third-year postgrad student for NTU. It's my pleasure today to give a presentation on my recent published paper on spin accumulation. So without further ado, let's get started. So firstly, let me start with what is spin orbit torque. Spin orbit torque, or SOT, is basically a torque that exerts on magnetization due to spin current. This spin current is commonly generated from two main phenomena, which is the spin Hall effect and rush-bar effect. However, due to the time constraint, I will only give a brief introduction on what is spin Hall effect. So, spin Hall effect is basically a creation of spin accumulation in non-magnetic material due to SOC, spin orbit coupling. It's a scattering effect where if we send an uncharged current into a heavy metal due to SOC, the electron will be scattered differently depending on electron spins. So on the bottom left is an animation of spin Hall effect, where we can see that the spins that are pointing into the screen is accumulated on top of the heavy metal, whereas the spin that is pointing out of the screen are accumulated in the bottom of the heavy metal. Therefore, this brings me to my main topic today. How can we measure the spin accumulation directly in the ferromagnetic layer? So there are several techniques that have quantified spin accumulation in the past few years. In 2016, Kush Raja has probed spin accumulation in Cu copper using STSM. However, here we are more interested in quantifying spin accumulation directly in the ferromagnetic layer because of the existence of spin backflow and spin transparency. In 2017, CSTEM managed to measure spin accumulation using MOOC. MOOC technique has been utilized by many other groups. However, there's a few drawbacks of MOOC, which is the optical signal detected from the spin accumulation is relatively small. Therefore, spatial imaging is challenging, and also the resolution of MOOC is limited by the optical diffraction limit. Lastly, in 2019, CSTEM managed to probe directly the spin accumulation in cobalt layer using SMCD. Yes, SMCD is accurate and a reliable technique. However, the setup for SMCD is not easily accessible as it requires the need of a synchrotron. So this brings us to our technique. In our technique, we utilize a DC bias harmonic Hall measurement to quantify the spin accumulation. So before diving into our technique, do allow me to give a brief introduction on the conventional harmonic Hall technique. So harmonic Hall technique is basically the measurement of the perturbation of voltage under SOT in the AC current and magnetic field. So the Hall voltage can be described by this equation over here, where the sine omega t term is the first harmonic and cosine 2 omega t term is the second harmonic. So in the IMA sample, the Hall resistance can be written in this form over here, where RA is a anomalous Hall resistance, which is proportional to MZ. RP is a planar Hall resistance, which is proportional to the dot product of MS and MY. HD and HX is a damping light field and field light field respectively. So the spin orbital has been characterized in our experiment, where we have used a structure of TA0PT and TI0PT. We have varied the thickness of TA and TI to observe the change in SOT efficiency. For the result, we can observe that the SOT efficiency increased with TA thickness. I can see on this graph over here. And this is nothing special since TA is a relatively strong spin source. Hence, the tendency to see an increase in SOT is no surprise. On the other hand, when we observe a negligible change in SOT efficiency when we increase TI thickness, since TI has negligible SOT as reported from other literature, this SOT mainly comes from the PT source itself. Coming back to quantification of spin accumulation, I would like to explain how do we quantify spin accumulation using our DC bias harmonic. Here is a cartoon explaining the spin accumulation model. So if you have a stationary field pointing up, the FM magnetization will follow the stationary field, in this case pointing up. Now, if you inject a current in the X direction, due to spin Hall effect, the electron will then be accumulated in the plus Y direction. Here, we can see that the magnetization in FM and electron spin are parallel to each other. Therefore, we can expect to see an increase in Hall voltage. Considering the other case, if we have a stationary field pointing down, the ferromagnet will follow the stationary field. The electron will still be pointing down since the spins is only dependent on the direction where we inject the current. The magnetization is anti-parallel to the electron spin, therefore we can expect to see a decrease in Hall voltage. So if we combine these two results together, we can actually isolate the signal purely for spin accumulation since the FM and magnetization will be cancelled out. So here's our setup of our experiment. First, we apply a stationary positive field AC current with a DC offset. In this way, we can ensure the electron spin to be polarized in a fixed direction, in this case plus Y direction. The amplitude of planar Hall resistance is then extracted from the first harmonic resistance. This PHE is inclusive of ferromagnetic magnetization RP and the spin accumulation delta RP. Like I discussed earlier, we can isolate this spin accumulation by applying an opposite direction stationary field. And by summing these two different positive field and negative field, we then can isolate the delta RP, which is contributed by the spin accumulation. Over here, the results show the amplitude of our first harmonic Hall resistance result. The solid symbol represents the stationary positive field plus HY, whereas the hollow symbol represents the negative stationary field minus HY. So let's take a closer look at the top two graphs in the red box over here. Since the current is injected in the plus X direction, the spin accumulated will be in the plus Y direction due to spin Hall effect. Therefore, the spin S will be parallel to M for the first graph and anti-parallel for the second graph. Just like I mentioned earlier, if the spin is parallel to M, the voltage will increase and vice versa. Here, we can actually see the amplitude of R omega in positive field to be higher than R omega in negative field. This is because of the alignment of the applied stationary field. Similarly, if you look at the bottom, two graph, the spin will be accumulated in the minus X direction, which is if the spin will be accumulated in minus X direction, because we send the current in the minus X direction, the spin will then be accumulated in the minus Y direction. And the amplitude when field is in minus Y direction is higher as compared to HY, positive HY. For DC equals 0, since we should see an identical amplitude, since the spin accumulation will be cancelled out when we plus them together. So the change of planar Hall resistance, delta RP, can then be calculated by averaging the magnitude in R omega for plus HY and minus HY together. So if you shape a range of DC current, we then can observe a linear change in delta RP, which is as expected, since current is proportional to the accumulated spin. Our experimental result is concluded on the top right-hand corner on the screen over here. The black and blue point represent the spin accumulation and damping light field respectively. From the first look at it, we can observe an obvious correlation between spin accumulation and damping light term. On the other hand, we have measured the spin accumulation in TSUPT and it reached up to 0.29%. To verify our experiment technique, we have compared our obtained value with system work where he had put the spin accumulation in COPT directly using SMCD, and our value obtained in TI-COPT is comparable to which system has obtained. This further validates our experiment technique. So, in summary, we have successfully characterized SOT in TI-COPT and TI-COPT using harmonic Hall measurement. We also observe a strong correlation between spin accumulation and damping light efficiency. Finally, we have successfully developed an all-electric technique to quantify spin accumulation in ferromagnetic layer directly. Yep, this comes to end my presentation. Thank you.
Thank you, Hani. You're well in time. So we have time for a couple of questions. Anyone from audience? Okay, so let me start. So you're applying an in-plane field, right? Either in HX or HY direction, right? So
yes, correct.
What is the effect of this in-plane field on the spin accumulation?
Sorry, can you repeat your question again?
What is the effect of in-plane magnetic field on the spin accumulation?
So since our sample is what is the effect of spin accumulation in in-plane field? So actually the spin accumulation doesn't depend on the direction of the magnetic field applied. It is dependent on the direction of the current where we inject. So we inject in the plus, since because we know it's V cross theta, where theta is the spin Hall angle of the material. If we inject current from positive X, we should have a polarized current in positive Y. So if we inject current in positive Y, we should have a spin accumulation in positive X direction. It's V cross normal to the surface.
Okay, then why there are two field directions?
Why there are two field directions?
Yeah, one is along the longitudinal, second one is in transverse. Yeah.
So you refer to this equation over here?
Yeah.
So so for the first case, the black solid, we apply a positive HY field. And then we apply when we apply a positive HY field, we finish the measurement, then we will obtain a RP. Maybe this slide will be clearer. Yeah. So when we apply a positive HY field, we obtain a result of RP plus delta RP. Then when we apply a negative field, we also obtain a result of RP plus delta RP. But the RP and delta RP in positive field and RP in negative field should be the same, just in opposite direction. So that's why I say that if we plus this, if we sum these two terms together, we can cancel off and isolate delta RP by itself.
Okay, so it looks like my question is a little confusing to you. I'm asking that what is the effect of Hx and Hy? You in the same cartoon, you are showing that you would apply field in Hx and you would apply field in Hy also. So what is the change that you can do?
So I saturate my field in Hy direction because in harmonic Hall measure we need a sweeping field. That's why to measure in plane field we need another sweeping field in plane direction. In this case, Hx direction, to measure the change in magnetization direction.
Okay.
The perturbation. Yeah.
Fine. Thank you. That's what I wanted to know. Yeah.
So
any other questions? No, it's okay. Fine. Yeah. Any?
No, I think let's move to.
Yeah. Thank you. Thank you, Hanyin. Yeah, please stop sharing.
Thank you.
So I request Wushu to start presentation. Hanyin, could you please stop sharing?
Yeah. So give me a minute. All right.
Can you see my screen?
Yes, please go ahead. You have 10 minutes.
Thank you. Hello, everyone. My name is Wu Shuo from NTU SPMS. I'm a first-year PhD student under Prof. Yuanxiang. Today, my topic is enhancement of spin orbital in PT cobalt HFO system while cobalt oxide orbital hybridization. So my presentation mainly includes 4 parts. First, I will give a brief introduction to spin orbital. Then I will introduce my current work, mainly consists of spin orbital enhancement in PT cobalt system with HFO capping layer. And I will introduce how the voltage-controlled oxygen migration affect the spin orbital efficiency. Then final part is the summary. So let's first see the introduction of SOT. So SOT means spin orbital. The toll on magnetization from the generation of spin current from charge current between FM and the HM layers. This spin current is generated mainly from 2 spin orbit coupling phenomena. First is a rush bar effect. So rush bar effect occurs in the FM layer. The current flow into the FM mantle and it will see equivalent magnetic field due to the electric field at the interface. And the second one is a spin Hall effect, occur in the heavy mantle and the current flows through the HM layer, which will lead to an accumulation of spin polarized electron at the interface. This table shows historical and potential developments in 3 SOT technology fields. It presents a rich array of fundamental physics, including bulk, interface, and many other phenomena. So what I'm doing now is this, SOT plus VCMA, voltage-controlled magnetic anisotropy. So let me introduce my current work in detail. One part is spin orbital enhancement. So in this work, we investigated the sample of PT cobalt HFO stack as our test sample, and the PT cobalt TI stack were also prepared as the reference sample for our comparison. This is a schematic configuration, and this figure shows the symmetric Hall bar course with 10 micron width and 100 micron length, fabricated with electron beam lithography and argon ion milling. These yellow areas are the contact pads. Then after the sample fabrication, firstly, we investigated different magnetic properties of our samples. This is the outer plane magnetic hysteresis loop of the thin films at room temperature. You can see the square loop indicate the strong PMA, and this figure shows the anomalous Hall resistance. It's clear the HFO sample shows a lower value of squareness in AH environment. We believe the decreased conservativity and the MS are closely related to the cobalt oxidation. This will be further verified by the following experiments. So then in order to evaluate the damping-like fields and the SOT efficiency, we do the first and the second harmonic measurement. This is a schematic of the whole voltage measurement setup by sweeping the in-plane field in direction HX and HY. And this is the whole voltages for HFO sample and the TI sample along the Z orientation, which means initial magnetization states being up and down. And by fitting the experimental data on the different current density, we can get the damping-like fields. And this is the HFO capping layer samples. The SOT efficiency is about 5.1, which is 60% higher than the reference sample. Then we investigated how the enhanced SOT efficiency affects the current induced magnetization switching. And you can see this figure, our HFO capping sample, the critical switching current reduced about 20% compared with the reference sample. We think the smaller switching current is mainly due to the higher damping-like torque efficiency, which is good for the low energy cost device for further applications. Then to confirm the assumption of cobalt oxidation between the cobalt HFO interface, we use VSM to measure different cobalt thickness films and get their MS. So you can see this figure. The MS of TI capping sample is always higher than the HFO capping layer samples. This indicates the oxidized cobalt results the reduction of the overall saturation magnetization of the cobalt layer. So there is cobalt oxide forming after the oxygen migration. Then we continue to see how the voltage-controlled oxygen migration affect the spin orbital efficiency. So you can see on the thin film PT cobalt HFO, we pattern the whole bar. Then the oxide layer HFO, the green part, which is 50 nano, and we also sputter a gate layer using couple. This is the image of device under microscope. And this is about AHE measurement result. You can see when gate voltage is from 0 volt to -4 volt, the weight of the vibration of these loops indicates the modification of the conservativity, but it remains unchanged when apply positive gate voltage. We should know that the negative gate voltage enables the electric field from the top layer to bottom layer. This means oxygen migration from up to down. And also based on harmonic measurement, we can get the damping-like field on the different gate voltage, and we can get the SOT efficiency. SOT efficiency similar to AHE measurement. We observe the SOT efficiency gradually decrease, then remains almost unchanged under positive voltage. So we believe that a larger electrical field enables more oxygen migration from HFO layer to cobalt layer. So to further investigate, we think this is enhanced by an interfacial oxidation of the FM layer. So
please summarize.
Yeah. So in summary, we experimentally demonstrate the enhancement of both damping-like torque and SOT efficiency with HFO capping, and the oxide layer causes the oxidation of the cobalt, which contribution to the interfacial rush-by effect. And we also apply different gate voltage to investigate how the electrical field will affect the SOT efficiency. So finally, we find a tendency. And we believe this study gives some contribution to realize controllability in SOT efficiency and develop a high efficient spintronic device. Then we can expect many other research on spin orbital phenomena will continue to transform spintronic applications for new technologies. Thank you for listening.
Thank you, Vishu. Nice presentation. Yeah, so please go ahead.
Yeah, just a very basic question. So why did you choose hafnium oxide rather than any other oxide?
Since the HFO's dielectric constant is higher than other oxides, so and our AJ system chamber have this target, so we try. I also try MgO, but I think HFO is much better.
Okay, thank you.
Any other questions? Ushu, in the similar lines, I would like to ask, I mean, your chamber, I know that chamber, so for sure you have MgO there. So why didn't you observe the similar effect with magnesium oxide?
You mean, did this have—
Why only HFO? Why didn't you see this cobalt oxide hybridization with MgO? If you could have tried,
with MgO cap,
yeah, go ahead.
With MgO capping, we also have this cobalt oxidation induced SOT enhancement, but compared with MgO capping, we observe the HFO capping can stabilize the PMA better, and which is really strong PMA. So we
can you quickly go to 9th slide once? I have a small question and then we can conclude.
Okay, 9. This?
Yeah. How do you conclude that the current required for switching is reduced by 20% from this plots?
Because I calculate the switching critical current. This is about 15, and this is about 17. So almost.
Oh, okay. But why the squareness is good in HFO compared to the titanium? Earlier in VSM, it is opposite. Okay, that you can just look into once. In VSM, you have shown the opposite behavior. But anyway, thank you. Nice presentation. Yeah, we should move on. So start. You may stop presenting. So I request Mr. Avinash to start presentation.
So to be a time, maybe Avinash can start at 2:56, which we have 2 minutes, 2-3 minutes for that, so that the rest speaker will be on the time. Is it okay, Dr. Chandra?
Yeah. So yeah. Why to rush?
Yeah, you can start sharing and then you can start.
Yeah, Avinash, you may start sharing. Yeah. Actually, I'm a little confused with this time. So 2:54 exactly, I'm unable to calculate in Indian Standard Time. So you please help me, Dr. Warren.
Oh, yeah, sure.
I think we can start at 2:55, maybe 1 minute faster, earlier is okay.
Yeah. So Mr. Avinash, you may start presenting. So 10 minutes, I will give you a call. Okay. Thanks. Avinash, are you speaking?
Audio is not working.
Your audio is not, we are unable to hear.
No, we cannot hear.
Yeah, we can't hear you, Avinash. If you plugged in some earphones, you may take out and try once.
No, we cannot hear you yet.
Still, we cannot hear.
Can we switch the speaker? Next speaker can present.
Avinash, would you like to try next? So that would be easier. So could you please stop sharing? So you can come next. Okay. So yeah. So that tells us that Saurabh Manna. So could you please start presentation?
Hello.
Yeah, we can hear you.
Okay, thank you for confirming. I'd like to share my slides.
Please go ahead.
Okay, so is it okay? Is it visible?
Yes, it's visible. You please go to the slideshow.
Yeah, slideshow. Okay. Okay.
Yeah, it's visible. Go ahead, please. Thank you.
Okay, thank you. Good afternoon, everyone. I'm Saurabh, and today I'll be talking about the field phase pinhole nano oscillators. So let's start from the very fundamental point of view. So we take a standard ferromagnetic non-magnetic bilayer sample, and if we apply an external magnetic field, this magnetic field exerts a torque on the magnetization, and because of that, magnetization starts precessing about the effective magnetic field. Now, this effective magnetic field includes both the external field and the fields originated from the internal origin inside the ferromagnet. Now, during this precision, the magnetization also experiences a damping torque, which tries to align the magnetization along the effective magnetic field. Now, if we pass a charge current through the sample, this can induce a Oersted field, which can also exert a torque on the magnetization. Now, if this bottom non-magnetic metal is a heavy metal, then due to the spin-orbit coupling, it can exhibit the spin Hall effect, where the electrons undergoes a transverse motion based on their spin, and as a result, a transverse spin current is injected into the adjacent ferromagnetic material. So this spin current exerts a spin orbit torque on the magnetization, which essentially depends on the spin polarization vector denoted by sigma here. So with all this torque, the magnetization dynamics can be quantitatively expressed by the Landau-Lipschitz-Gilbert equation, which is shown here. So the consequences of this spin orbit torque driven magnetization dynamics are several. Among them, like it can switch the magnetization to the spin polarization direction, as is demonstrated by this paper. But there is also an intermediate phenomena where this spin orbit torque exactly compensates the damping torque, and in that case, the magnetization undergoes a completely undamped or the sustained precisional motion. We call it the magnetization auto oscillation, and these type of devices are known as the spin Hall nano oscillators. So we'll be focusing on this spin Hall nano oscillators. Now, these spin Hall nano oscillators can be used in designing the brain-inspired computing architectures, or it can also be used as the microwave generation sources, which can be useful in wireless communications. Now, the voltage control oscillators and the spin Hall nano oscillators have significant difference in terms of their speed and size. For example, the spin Hall nano oscillator shows higher speed as the dynamics occurs in the nanosecond or sub-nanosecond time scale, and also its size is in nanometer scale. So there are several geometries available for the spin Hall nano oscillator designing. For example, the nano gap based geometry, the nano constriction based geometry, the nano wear based geometry, and the nano pillar based geometry. Among them, we have chosen this nano constriction based geometry as it's easier to fabricate compared to the all other geometries, and also it gives us the opportunity to use a very low input current. So we designed a platinum permalloy bilayer with a 50 nanometer constriction width, and we injected a DC current so that in the platinum, from the platinum metal, due to the spin Hall effect, it can inject a transverse spin current into the adjacent NIFE layer. And now we studied this magnetization dynamics of the auto oscillation using the micromagnetic simulation in MUMAX. So we map the current density distribution in the platinum layer, and we have seen that due to the spatial geometry, it has a significant non-uniformity in the current density distribution. And we also mapped the Oersted field distribution in the permalloy layer. So with all these, we have achieved the oscillation, and this is the oscillation profile for input current of 1.6 milliampere, and the external field is 0.1 Tesla at a 75-degree angle with respect to the current. Now the question is, if we want to use it in real life device purpose, applying this external magnetic field is not at all a good idea. So is there a way to remove this external field and to achieve the auto oscillation? And the answer is yes. We propose that using the anisotropy field, we can achieve the same auto oscillation in this nanoconstriction based device. Now in the permalloy layer, there is no anisotropy in general, but we can actually induce some magnetic anisotropy, as is demonstrated by my colleague Dr. Rohit Medwal in this RRL paper. And he has shown there that there is a uniaxial anisotropy induced in the permalloy by modifying the deposition scheme. So we have used this anisotropy in our simulation, and we defined an easy axis, and with this we achieved the auto oscillation in a bias free condition where the external field is 0, as you can see. Now the question is, what is the anisotropy energy constant? The Ku is here the uniaxial anisotropy constant, which can also be termed as the anisotropy energy per unit volume. So to study the role of this Ku, or to see what is the optimum value of this Ku, we studied the Ku dependent behavior. So as you can see in this left graph, that if we increase the Ku, so the oscillation frequency changes. So we can say that by proper anisotropy energy, with this anisotropy energy, we can actually tune the auto oscillation frequency of the spin Hall nano oscillator. There is also another important result, is that in the right side graphs, if you see that as we increase the anisotropy energy density, the Ku value, the threshold current for the auto oscillation is significantly reduced. As you can see from these graphs, as you can see here, that for lower anisotropy, the auto oscillation has not started yet, but for the same current, same input current, for higher anisotropy, the auto oscillation has started. That means we are able to achieve a low threshold input current value for achieving auto oscillation, and this gives us the opportunity to design low input power oscillator devices. So to understand what is the physical origin of this kind of behavior, we mapped the effective field at this nanoconstriction region. So we see that in the effective field region near the nanoconstriction region, there is a confinement, as is shown by these blue arrows. So we see that there is a change in the effective field behavior, and because of that, there is a confinement of the auto oscillation of the oscillation near the constriction edges. And as we increase this Ku value, the anisotropy value, this confinement region shrinks down. And what is the consequence? The consequence is, once the auto oscillation by some input current, if we excite the magnet, if we pass some input current, then once the oscillation starts at these constriction edges, it is no longer confined in the around the constriction region. The spin waves generated from this auto oscillation, they get spread out around the constriction region. And because of this smaller confinement, it is much easier to disturb the magnetization to start the auto oscillation. And this explains that why we achieve a lower threshold current once we start increasing the anisotropy energy. So with these observations, we can conclude that we have achieved the field-free auto oscillation in nanoconstriction based SHNOs, and this induced anisotropy can actually enhance the output power and the efficiency of the oscillator, as we can tune the threshold current density of the oscillator by tuning the anisotropy. And finally, this particular nanoconstriction geometry, this plays an important role in determining the characteristics of these field-free auto oscillations. So with this, I would like to thank you for listening to my talk, and I'd like to also thank my group members at PAL at NIE, Dr. Rohi, Dr. Surbi, Dr. Jevas, Avinash, Shilpa, and Mayank, and of course Professor Rawat. So thank you. So yes, now I'm open to questions.
Yeah. Thank you, Saurabh. The floor is open for questions. Yes, Saprit, go ahead.
Hi, Saurabh. It's a nice talk. So on your previous slide, right, I have like a quick question. So since I can understand why the frequency is increasing and why the current is reducing, but can you comment on the amplitude of your precession, of your oscillation precession? I think that would decrease with the increase in KU, and it would become more difficult to detect these oscillations.
That is the point I discussed actually, because as you see that with the increasing KU, as you see that this confinement region is shrinking. So that's why once the oscillation starts, it starts also spreading out from the constriction region. And that's why actually we see the opposite behavior here, because we get higher amplitude of the oscillation. So because these spin waves generated here, they are no longer confined in this region, and they start spreading out around the constriction. So we get a much bigger oscillation volume. Whereas for smaller anisotropy, the oscillation is confined in this region only.
Okay.
So that's why the power is.
Thank you.
Yeah. So this is actually the nanoconstriction geometry effect and the anisotropy, of course.
Okay. Thanks. Thanks, Saprit. Any other questions? If not, Saurabh. Okay, so spin Hall oscillators, they're good, but the overall the power that you can achieve is in picowatts. I think. Yeah. Okay. So do you think that as you keep on saying that, is it really energy efficient?
I like to point out that actually I did not do any experimental studies. So these are all the micromagnetic simulations. So in these micromagnetic simulation, I do not have any direct access to see how much power we are actually extracting. We are saying that we are predicting.
I just wanted to know your comment since you're working, and also the second point, which just a comment that you are unable to tell how the line widths are changing with as a function of anisotropy so far. Because line widths are also, the quality factor should be very good.
Yes, that's true. So that's true.
I would suggest that you look into those two aspects. It's not only the amplitude, the line width also matters a lot. Okay.
Yes. Thank you for the direction. I'll just definitely work in the direction to see the variation.
Thank you. Okay, so let's move on. Avinash, would you be able to present now? Saurabh, could you please close? Thanks. Avinash, you are there? No. Could you please speak first? No need to share. Could you please share? Speak. We are still unable to hear you. Okay. So in that case, Avinash will be the last one to present. So Avinash, please stop it. Presentation. You fix it first. You will be presenting at 4:06 p.m. So I request Saprit to start the presentation. Avinash, please fix it before 4. Yeah, Saprit, go ahead.
Okay. Second. Okay. So good afternoon, all of you. I am Saprit from NTU. In this talk, I would be talking about how to tune the physical properties of fermion via interatomic displacements. So magnetic fermion are considered to be chiral spin textures, and because of their promising properties, they have been proposed for memory and computing devices, where the fermion is nucleated at one end of the track and it moves towards the other end and it detects there. Now, this fermion can exist in either a sparse state or a dense fermion state. And the dense fermion state is more propitious for high density memory and computing devices. However, to achieve a high dense fermion state, one requires a subtle combination of magnetic properties, especially the ratio of DMI over the product of effective anisotropy energy and exchange coupling energy has to be higher. The ways by which a DMI can be increased involves reducing the thickness of ferromagnet, achieving a smooth interface. But this also results in increasing the anisotropy, which limits the fermion density. In my talk, I would be talking about a way where we have achieved high DMI without increasing the effective anisotropy energy. Our method is based on manipulating the interfacial interface of the material, where the DMI and K effective are the both interfacial phenomena, and hence we can manipulate these two properties. So here we have used two methods. First is temperature induced modification, where we have this modification induces the diffusion of atoms at the interface. Second is via helium ion irradiation, where it introduces the intermixing of atoms at the interface. And we were able to observe promising results using the helium ion irradiation. Now, this study has been carried out on cobalt iron boron 8 repetition sample, which was deposited using Singulus Timaris tool. Here I show the hysteresis curve of the pristine sample, and this sample shows a very high dense state at zero field with the periodicity of 168 nanometer. On increasing the field imaging, magnetic field of imaging, we observe a sparse fermion state around 39 millitesla with a size of around 145 nanometer with a fermion density of 11 fermions per square meter only. Now we move to our first method, which was annealing. So we have changed the temperature from 150 degrees Celsius to 300 degrees Celsius. The annealing has been done for an hour. Here we observed the magnetic properties first. And for that, we have used VSM, where we have able to see that the effective anisotropy energy is increasing with increase in the temperature. Now, this increase in the effective anisotropy energy might be the reason because of the crystallization of the cobalt iron boron, which is causing the smoothness of the interface. Moreover, we have seen that the magnetic remanence shows an increase at 250 degrees Celsius and 300 degrees Celsius. That means the dense magnetic states which we were observing at zero magnetic field is not equivalent anymore. Further, the saturation magnetization also shows a high increase in the value from the 150 degrees Celsius, which is because of the migration of the boron, which is a well-studied effect. Further, we have calculated the uniform anisotropy energy, which can be calculated using the formula, which shows a considerable substantial contribution from the effective anisotropy energy, where the magnetostatic energy is decreasing, but it still remains constant. Now, before measuring any other property, we have measured image the magnetic textures first. And here I'm showing the zero field magnetic textures of different annealed samples. And then, as can be seen, with increasing the annealing temperature, the magnetic textures are becoming less dense. And this can be translated into the periodicity, where the periodicity is increasing around 168 nanometer to 420 nanometer. For higher temperature, annealed temperatures, we were not able to observe any magnetic textures at zero field because the shape of the loop becomes square and there are no magnetic textures here. Now, if for these samples, if we increase the magnetic field and measure, image the textures, we saw that the magnetic fermions density has been reduced as increase of the annealing temperature. From here, we can say that the annealing is not a viable method to increase the fermion density. So we move to our next method, which is helium ion irradiation. So the helium ion irradiation was done by using an ultra compact helium facility. We have used ion energy of 20 kilo electron volt. First, to understand the effect of the irradiation, we have carried out Monte Carlo simulations done on a 8 repetition cobalt iron boron sample, which mimics the experimental use sample. Here, the Monte Carlo simulations predict that the cobalt iron boron or the ferromagnetic atom can migrate into the platinum layer. Moreover, the lateral displacement of these atoms is higher than the vertical displacement. That means that these atoms can displace more into the lateral direction as compared to the displacing into the platinum layer. Now, based on these results, we can say that by varying the dose, we can vary the atomic displacement. Now, to experimentally corroborate this intermixing, we have carried out cross-section TEM. Here I'm showing the 8 repetition pristine layer. If I zoom in, you can see a very weak cobalt iron boron layer sandwiched between magnesium oxide and platinum. Now, on this sample, we have carried out helium ion irradiation. And first, I am showing here the EDX, energy dispersive X-ray spectroscopy, cobalt mapping. And this is a pristine sample. On a very low dose, you can see that between 2 adjacent cobalt layer, there is cobalt atoms displaced after the irradiation. On a 4 times higher dose, you can able to see that the displacement of the cobalt atoms even from the ferromagnetic layer has been increased. So from here, we can infer that by varying the dose, the cobalt displacement is varying. And to further understand, we have also carried out of scenes. Because of the time constraint, I'm not going to show that. But in conclusion, the structural properties varies that after irradiation, we were able to see that the intermixing of atoms at the interface, moreover, the atoms like boron are migrating between the ferromagnetic at the interstitial sites of the cobalt and iron. Now, this change in the intermixing of the interface will causes the change in the interfacial properties, whereas the migration of the boron will cause the change in the bulk properties like saturation, magnetization, and exchange energy. To experimentally realize the effect of this, we have actually done the hysteresis curve studies starting from the effective anisotropy energy. As can be seen that with increase of the irradiation dose, which we restricted into 12 into 10 raised to power 18 ions per square meter to prevent the degradation of the ferromagnetic layer, that the effective anisotropy is reducing, which can be understood because of the disordering of the interface. Moreover, the saturation magnetization is also increasing, which shows a higher value at 8x. And further, we have calculated Zaloshinsky-Moria interaction using the Breuin light spectroscopy, which also shows a high value at 8x value. Now, the exchange coupling, we have used micromagnetic simulations, which also shows a similar trend, which was quite interesting to us, that how the magnetostatic energy is affecting the Zaloshinsky-Moria energy, as well as the exchange coupling energy. Now, we were able to see the difference in increase in the DMI without enhancing the effective anisotropy. Now, the question comes, are we able to see the decrease in the fermion diameter, fermion density? So for this one, we have carried the MFM imaging, and we were able to see that the fermion density decreases as the irradiation dose is increasing. On fitting these fermions, we saw that the fermion density is increasing by 5-fold. Moreover, the fermion size reduces almost by 50%, reaching up to 70 nanometer for these doses. To compare these between two results, we saw that the irradiation, unlike annealing, can increase the fermion density as well as it reduces the fermion size. Now, this irradiation can be used for further potential applications. For example, the increase in the fermion density can be understood because of the decrease in the domain wall energy, which gives you the delta E, which is like the energy difference, which can be used for suppressing the fermion Hall effect. In normal fermion motion along the wire, it observes from the fermion Hall effect, and it has some annihilation at the edge. Whereas if you use this ion irradiation, and you can form energy barriers which will restrict the fermion along the edge of the wire, and you will be able to see a guided motion. This can be further explored for multiple fermion motions, where you can pack multiple fermions with next to each other and can observe high density devices. So besides this, as I said, we can also tune the static fermion physical properties, which can also give for high density states. And this brings to the end. I would be thankful to my collaborators, my professor, and my other co-authors. Thank you.
Yeah, thank you, Saprit. Very interesting. So the overall imaging is magnetic force microscopy, is it?
Yeah.
Yeah. Okay. Fine. Okay. So now the talk is open for questions and comments. Saurabh, you want something?
Yeah,
go ahead.
I want, yes, Sabrit, hi, nice talk actually. I'd like to just ask, I think because of my limited knowledge, I couldn't understand. So could you explain that could you understand that these are the skarmions from seeing
okay.
those?
Okay, so apparently, okay, so that brings me to my first slide actually. So ideally, the skarmions are considered to be this 360-degree domain walls actually. Okay, so here you observe that okay, so, and then for the experimental studies what have been done, normally you have a substantial value of Zaloshinsky-Moria interaction, which makes this bluish part, which is smaller as possible. Okay, now because of the studies and different values of DMI, you have like three categories. One is the bubble-like skarmions. Okay, skarmions like bubble, which is more than 1 micrometer. Then comes the skarmion-like structures, which is around a few hundred of nanometers. And then there are skarmions which is like sub 50 nanometer, like less than. So it's like a one single domain where there is no single, a big chord, just a continuous 360-degree domain wall. So the skarmions which I am showing is around 75 nanometer, which is somewhere in between the actual skarmion and the skarmion-like bubbles. I think that answers your question.
So you measure the diameter, right?
Yeah.
So from the measuring the diameters.
Yes. So for measuring the diameter, we have actually done two-dimensional Gaussian fitting for the all single skarmion, and from there we have measured this diameter.
Okay, I see. Thank you.
So is there time to ask for another question?
Yes, sure, please.
Let me see if I get your presentation correctly. So you are saying that by irradiating your sample with helium, you are essentially making the domain wall energy lower. So
yes.
Therefore, your skarmion, it's easier to form the skarmion. Is that correct? Is that the gist of your presentation?
Yeah.
Okay. Yes, thank you very much.
Okay.
It sounds to me like it's a roundabout way of creating it. Why don't you start with some material that is with a low domain wall energy in the beginning, so then you don't have to.
Okay, because it's quite a actually a challenge to get material which starts with, because DMI and effective anisotropy both are interfacial phenomena. Okay, so if you, let's say, have a smoother interface which promotes both DMI and effective anisotropy, both values will be high. Now, most of the studies, for example, in case are the effective is quite strong that it dominates the domain wall energy. So in that case, even if we start with sample where the domain wall energy always is a point of issue where we have to compensate density to a certain value. So that's why I showed, for example, in the states where they have varied the make the interfaces more smoother, they were able to limit the skarmion density around 20 skarmions per square meter or something. So here we were able to achieve around 50 skarmions per square meter.
Anyways, yeah, so thank you very much.
Per square meter, you mean to say?
50 skarmions per square meter. Square micrometer, sorry. Square micrometer.
Fine.
My bad.
Right.
Yeah.
Okay, so we have to move on. So
yes,
thank you,
okay.
Sabrit. Yeah, so I request William to start presentation.
Okay, can you see my slides?
Yes, go ahead. You have 10 minutes.
Okay. Thank you for giving me the opportunity to present. Good afternoon. My name is William. I'm from NTU, and I'm going to talk about domain wall device as artificial neuron for neuromorphic computing. So neuromorphic computing is a more power efficient platform for AI because it is modeled after the brain. And the brain consumes much less power than our state-of-the-art supercomputer. And since the neuromorphic computing is modeled after the brain, it has two main components, the neuron and the synapse, which functions as the processor and the memory respectively. So far, there's been more work done on synapses, but in this talk, I'm going to focus on neurons, specifically domain wall-based neurons, which should exhibit the leaky, integrate, and fire properties. I'm going to explain them in the context of a domain wall device. The first property is called the integrate function, which is the ability to push the domain wall by applying current. And then the next is the firing function, which happens when the domain wall has passed a certain threshold position. In that case, I want to see a change in the read signal. And finally, is the leakage function, which happens in the absence of current. In that case, I want my domain wall to automatically return towards the starting position. In my research, I want to first achieve the integrate and leakage functions. I can do that by utilizing a synthetic antiferromagnetic structure where the free and the pin layers are mostly antiferromagnetically coupled to each other. I say mostly because there is a region on the left here which I want to be ferromagnetically coupled, because then I can nucleate the domain wall without having to apply any magnetic field. I can achieve my integrate function by applying current and pushing the domain wall towards the right via spin transfer torque. And once I switch off this current, due to the antiferromagnetic coupling between the top and the bottom layers, the red domain would expand, which would automatically push the domain wall towards the left, back to the initial position. That is the leakage function. We did some simulations to see whether we can achieve the integrate and leakage functions. Graph on the right is a domain wall position against time graph. This 128 nanometer corresponds to the initial position of the domain wall, which is this point on the drawing. 384 nanometers is the threshold position, corresponding to this point on the drawing. I start from initial position, I apply current. Current is pushed towards the threshold position, 384. That is the integrate function. Once I switch off the current, the domain wall would automatically come back towards the initial position. That is the leakage function. The stronger my antiferromagnetic coupling between the top and the bottom layers, the faster it comes back down. Just to show my point a little bit clearer, here is a video. So I apply current and domain wall is pushed towards the right. That is the integrate function. The moment it reaches 384, I switch off the current and then it automatically return towards the initial position. That is the leakage function. And so in the simulations, I have demonstrated both integrate and leakage functions. Let's see the experiments. I utilize a cobalt palladium multi-layer sample. If you look at this red color hysteresis loop on the right here, this corresponds to the out of plane hysteresis loop. You can tell that this cobalt palladium multi-layer sample has synthetic antiferromagnetic properties. Using optical lithography, I fabricated a microwire of length 100 micrometer, width of 5 micrometer. The thickness is just the thickness of the entire sample minus the substrate. I apply a total of 10 pulses. Each pulse is 2 seconds away from each other. I represents the current strength. PW is the current pulse width, which is the duration of the current pulse. So the current strength is varied from 0.01 ampere all the way to 0.03. Pulse width is varied from 1 microsecond all the way to 6. I have tried every single combination, but in this talk, for the sake of time, I'm only going to talk about specific cases. So before that, the first step is to apply a really strong magnetic field in a plus Z direction so that I can saturate the entire system. Then I immediately reduce that field to around 2.3 kilo oersted, still in the plus Z direction, because at that field, I can nucleate domain walls in the free layer, the top free layer. And after that, I will apply current pulses and observe what happens to the domain wall under curve microscopy. So in this case, I'm applying a current strength of 0.03 ampere, and the pulse width is 6 microsecond. This is a video, and it may be important to take note of this pulse word here, because whenever I flash this pulse word, it means I'm applying a current pulse. And you may want to take a look at the domain walls, see how they are getting pushed. Okay. So if you see, whenever I apply a current pulse, domain walls get pushed back, specifically like this. So these are the screenshots from this video. And when I apply current pulse, the domain walls get pushed back, which is the integrate function. After a short amount of time, the domain walls come back. That is a leakage function. But one interesting observation is that the domain walls actually move in opposite directions, which is not indicative of the spin transfer torque effect. Because if spin transfer torque is dominant, then the domain walls would move in tandem. But in this case, the domain walls are moving in opposite directions. So one possibility is that this is due to Joule heating. But in order to determine if Joule heating is dominant or is any significant effect or not, we did some minor loop measurements. This black curve is the reference case. It's the field-only case. The rest has current pulses, and the details of these current pulses are here in the legend. If you take a look at the changes to the coercivity, you realize there is significant reduction in coercivity, which is an effect of Joule heating. And if you look at the exchange field, now albeit the exchange field changes isn't as significant as coercivity, but there is still a reduction nonetheless. And it's reduced means that there is a weakening of the antiferromagnetic coupling between the top and the bottom layers. That can also be due to heat. And so the idea of how heat can push the domain wall is, first, it weakens the antiferromagnetic coupling between the top and the bottom layers. But at the same time, I'm still applying a field in a plus Z direction because I want to nucleate the domain walls. So weakening antiferromagnetic coupling strength, but the whole time the field is still there. So the Zeeman effect would dominate. And in that case, my rate domain would expand. That would push the domain walls away, which is what we observe in the videos and also in the screenshots. That is what gives us our integrated function. And after some time, as the heat dissipates, then the Zeeman effect no longer dominates, domain walls come back by themselves. That is the leakage function. And so all in all, in the simulations, we have demonstrated integrate and leakage functions, and so does the experiments. And even though the integrate function is achieved by Joule heating, the current density is comparable to spin transfer torque. So actually, this synthetic antiferromagnetic design is a potential candidate as an artificial neuron for neuromorphic computing. Thank you for your time.
Yeah, thank you, William. Now the floor is open for questions.
Yeah, I do have a question.
Please,
it's a very interesting phenomenon. So you're saying that the domain wall motion is primarily driven by Joule heating. So if that is the case, if you use a smaller current, let's say, so then the Joule heating should potentially be smaller. So do you observe that the domain wall moves slower in that case?
Oh yeah, definitely. So these are, I varied the current strength as well as the current pulse width. So if I reduce the current strength, right, if I observe in this case, this is the case that I showed you just now, 0.03 ampere. But if I reduce it to 0.02 and 0.01, especially 0.01, you see no difference. 0.02 ampere, you see a little bit of pushing, just a little bit, like from here to here, it's pushed slightly. And also, if I vary my pulse width from 6 microseconds down to 3, down to 1, you also notice there is a less obvious integrate and leakage function.
I see. Okay. Thank you so much.
You're welcome.
Thank you, William. Yes, Vijay, go ahead.
What was the S by N of your system? Signal to noise ratio.
Signal to noise ratio.
Yeah.
We didn't measure the signal to noise ratio.
Okay. And you mentioned in your slide 12, you mentioned field values up to 4 digit. So which instrument did you use to measure cursivity?
Which instrument we use to measure corrosivity? We use the magneto-optic curve effect. We use the curve microscopy.
Is it able to provide corrosivity up to 4-digit after the like 10⁻⁴ order up to that scale?
10 to the power of 4.
Yeah, -4.
10 to
you
minus
can go
4.
to your slide 12. Yeah, here after the point you are having 4 or 5 digits.
These
Yeah, 5
digits,
digits. Yeah.
These digits are calculated based on what I got in the data file from the curve microscopy. They do give they do give a lot of decimal places.
So this doesn't indicate accuracy of your data. Okay.
Yeah, it may not be. Even Earth magnetic field is in that.
Yeah,
because I'm averaging out.
Just, yeah.
I'm averaging out both points.
Yeah, you could have just stop it after 1 digit also. That's fine. Yeah. Any more questions? So I just want to know quickly, you might have mentioned, but I missed that. What is the speed of the domain wall in this SAF?
The speed of the domain wall. You mean the speed at which the domain wall is getting pushed, or speed of the domain wall as it comes back?
Either way, I just wanted to know the speed of the domain wall.
Okay, so the speed of the domain wall getting pushed, right, is because the thing is, if you look at this screenshot here, right, it goes from 0 to 0.1 seconds. So the domain wall can be pushed anywhere between those timing. So it will be at least whatever this distance is being covered. So which is why I don't want to mention that, because I don't have any.
No, I got it. Yeah. That's good. Now I can understand that you're being very honest, and then
yeah.
Thank you. So we have to move on. Thanks, William.
Yeah.
Thank you, William. So I request Yuanxiang.
Hello. Can everyone hear me?
Yes. Yeah. Please
okay,
share.
I will share my stuff. Oh, the host does not allow me. I cannot share because the host need to allow me to.
Dr. Warren, could you please help?
Yeah, allowed.
Okay.
I think he rejoined, and that's why. Yeah.
Oh, okay. Can everyone see my desktop? See my slide?
Yes.
Okay. Thank you, everyone. I appreciate this opportunity to share my research. Actually, we are very new to this area, and we are very happy to hear some of your comments and advices. Okay, this research focuses on the tunable magnetic bubble in nanostructured synthetic antiferromagnet, and my supervisor is Yuanxiang. I'm from NTU, and here is a brief introduction. Actually, the majority of the spin texture are actually determined by the spin-related Hamiltonian, no matter it's ferromagnet and antiferromagnet. If we look at this, the intrinsic metal, if it's a paramagnet, ferromagnet, antiferromagnet, what distinguishes them is the J related with the spin exchange interaction. This is the intrinsic one, intrinsic metal. But actually, there are some other, a lot of kind of. It's called synthetic antiferromagnet. It has an interlayer antiferromagnetic interaction induced by the ruthenium. And apart from this, actually, Sabri has also mentioned that there is actually another very unique spin texture. It's called skyrmion. And what determines the skyrmion is a Hamiltonian, is the DM interaction. It's a crossing asymmetric interaction between two spins. Actually, it's physically is induced by the spin orbit interaction or related property. But what makes skyrmion so special is it has a gradient transition spin from downwards to upward. It's a gradient chain. And experimentally, if we want to realize to achieve this skyrmion, we need to use this heavy metal layers, uranium or tantalum, and coupled with the cobalt layers. And we can observe this dot-like spin texture, which is a skyrmion. And also some other researchers also mentioned that if we etch some of the layer into this nanostructured shape, like the circular nanodot, we can also observe those very unique gradient transition textures. and via the nanostructure. So my research is, so what if we combine the nanostructure and also the synthetic antiferromagnet? What if we combine them? What can we get? And here is our sample. So we use sputtering to deposit multiple layers, and then we etched all the layers above the ruthenium into a circular nanodisk. The top and bottom tantalum is used to prevent oxidation. Then we have the top cobalt PT and bottom PT cobalt ferromagnetically. It's a perpendicular ferromagnet. And this is our sample structure. Then we etch the bottom layer into a whole bar crust because we want to measure the transport result. And here is a top view of the SEM and the optical image. So in this work, we were actually changing the shape of this nanostructure, both the diameter of the nanodisk, the repeats of this bottom layer, bottom PT cobalt, and the disk, the diameter of the number of the nanodisk. We were changing this, and we were trying to see what's going on. Okay, since the nanodisk is very small, it's less than 1 micrometer. So the general MOC method cannot give a very accurate result. So we choose to use anomalous Hall effect. And we were actually sweeping. We can observe this hysteresis, but it got multiple switches. So if we want to know what the spin textures are during this step, we use another technique, MFM. So what MFM tells us is, well, if the nanodisk and the bottom layer, their spin are along the same direction, it gives you a dark color. Otherwise, it gives you a relatively bright color. So, and this one, 0.4 Tesla, all the spin are upwards, so the center is dark. Similarly, 1.2, negative 1.2 Tesla, all the spin is downward, is dark. If we sweep it, after it crosses the first switch, the top of the spin are flipped. So it got antiferromagnet coupled, and the center become bright. And after it crosses the corrosivity, we can see the top, the spin uncovered, the spins in the bottom layer, which are not covered, are flipped. After it flipped, it got this kind of gradient transition from the center upwards and gradually transitions to downwards to the outer side. And we can see that if we check this MF image, inside is bright and together it's also dark. So there is both bright and dark area inside the nanodisk area. It's like a bubble. So we were trying to check whether the bubble the spin texture of the bubble follows the spin texture of the skyrmion. So what we do is, so this is our spin, the MFM measured, the MFM signal of the nanodisk, 1 nanodisk. And we have a simulated nanodisk. And with the skyrmion, we added purpose. And we checked and we find that these two MFM signal across this line are very similar. So we would like to propose that the spin texture of our bubble is actually the skyrmion bubble. So what we further do is we check we measure the whole anomalous Hall effect at different temperature, and we found this skyrmion bubble region is very stable. It has little change over from 300 K to the base temperature. It had no change. It's very robust. And finally, we measured the anomalous Hall effect with different shapes, different nanostructure shapes. So firstly, this one column, we decrease the diameter of the nanodisk. And even if it's as small as 200 nanometer, this skyrmion bubble region is still there. It's unchanged. Although it becomes smaller, but it's still there. It's very stable. And if we increase the number of the nanodisk, what's different between this and this is 1 nanodisk, and we have 9 nanodisks. If we have more nanodisks, we theoretically have more skyrmion bubbles. So when the skyrmion bubble transits, more nanodisks give a much sharper transition. This is what we found up until now. And here's a basic conclusion. And we got multiple states, multiple spin textures in this nanostructure synthetic antiferromagnet. And we got a robust skyrmion-like bubble texture. And I appreciate my guide from supervisor and the sample preparation from Professor Martin. And thank you for your attention. And now I'd like to take some questions.
Yeah. Thank you, Mr. Ki. Yeah. Now the floor is open for question and answer session. Yes, yeah, please go ahead.
Hi, Wang. Hello. Thank you for the presentation. So I have a doubt because I don't have much idea about anomalous measurement, Hall measurement. Just want to know that when someone measures the anomalous Hall effect, so whether there any contribution from the normal Hall effect or someone has to extract that.
Yes, actually, yes. Actually, a normal Hall effect is always there. You can always see the normal Hall effect. And you can see if we check this picture, this is not a straight horizontal line. There's a tiny little upward. But actually, this one is much smaller than the enormous Hall effect. So in this case, we don't need to subtract it.
Okay. Thanks.
Any other questions? I'm asking some naive question because of my weak understanding is that, but there is one, recent observation that skyrmion can give you the topological Hall effect. I think you might.
Topological. Oh, yeah, I also noticed that, but actually we didn't capture that topological width, so we were still doubt whether whether that bubble is a skyrmion or not.
That's what I believe, that whenever you are seeing a skyrmion or a kind of a skyrmion like a magnetic bubble, so you need to estimate that how much is the contribution from the topological. So that,
that's a good.
Okay, but you don't need to take my word as my word because.
Well, that's a good point. We need to consider.
Yeah. So Mr. Key has ended the talk very well. Within the time, so we have time for 2 more questions. Anyone?
Okay.
So can I ask a simple question?
Sure.
Right. So the only direct observation you have of the skyrmion is MFM imaging. Is that correct?
Actually, we try to propose that it's like a skyrmion, but we don't have any solid devices characterization over the DMI. Oh, to my knowledge, if we want to prove that this bubble-like texture is a skyrmion, we need to estimate its DM interaction. But actually, in this work, we didn't. So we just want to propose it's possible skyrmion. But currently our observation is the skyrmion-like texture via the MFM. So what's your next question?
What is the size?
This is a 400 nanometer.
So it occupies the entire dot.
Oh, you mean what's the size? You mean what's the size of the skyrmion?
Yeah, so it's the same size as the dot.
No. When it just nucleates, it's the size of the skyrmion. But when we increase the field, you see that the RXY, which the anomalous Hall resistivity is decreasing, which means we were squashing this skyrmion like bubble. So finally, initially it's the same as the nanodisk size, but if we further squash it, it becomes much smaller.
Oh, okay, I see. Okay.
But we still have to say that we don't have very solid evidence to prove that this
you need to do some DMI measurements on DLS or something, then you will be.
I think that's what we should do.
But you only see one skyrmion per dot, correct?
Yes.
Okay.
Do you have time for one more question?
There is a small suggestion that if you apply magnetic field in 2 directions, you may see that the shrinking and then expansion without annihilation. Maybe that could be one kind of a lead. I'm not saying that is the way to do it, but you may just think about it. But for that, you need to have in situ out of plane magnetic field to do this.
Yes.
Yeah. But a very interesting talk, Mr. Thank you.
Yes, Prem, you can ask. You have time.
So my question is about your MFM in magnetic field. You are applying field as high as 1.2 Tesla. Is your tip magnetization flipping?
Yes, of course. I think the corrosivity of the tip is, if I'm not wrong, is about 200 OE. So after 200 OE, the tip magnetization is flipped. The magnetization of the tip is flipped. 200 OE, which is about 0.02 Tesla, it will flip.
Okay.
So
yeah. Dr. Varun, should we move on or you have any?
Yes, I think we can move.
Oh, yeah.
So I will stop my sharing.
Yeah.
Thank you. Thank you.
So I request Yakun to start presentation.
Okay. Start sharing my screen. Yes, could you please see my screen?
Yes, it's visible.
Okay. So I will open my video. You can also see me. Okay.
Yes, please.
Yes, okay. So good afternoon, everyone. It's my pleasure to share my results on the observation of the three-dimensional spin texture in well semi-metal telluride 4. I'm PhD student from US Department of ECE. So where semi-metal is predicted with a large charge to spin efficiency, since it not only has a spin momentum locking and surface, but also has a conductive bulk state with strong orbital coupling. Besides, it also predicts to have the Z-spin when the current is flowing along a axis, which is allowed by the symmetry. Currently, the Z-spin from well semi-metal is observed in exfoliated tungsten telluride and also CVD tungsten telluride with a method of STFMR. Compared to the conventional binary well semi-metal, tungsten telluride and molybdenum telluride, their ternary family member tellurium iridium tellur 4 is more conductive, which is supposed to have a high spin conductivity. In this work, we use flakes mechanically exfoliated from a single crystal of TD phase telluride tellur 4. With the help of microscopy and lemma, the rectangular flakes were chosen and patterned to hold bar along a-axis. Then the BMR measurement is adopted for spin texture detection. BMR, the short for bilinear magnetoelectrical resistance, which can be seen as the kind of UMR, but the difference is that the amplitude is linearly dependent on both current and the field. The second harmonic RXX from BMR measurement can reflect the spin angular momentum direction. Why? Here I will give a short explanation. For positive charge current, the first harmonic spin angular momentum will generate from the minus K space. However, the second harmonic current will generate both from K and the minus K spin. When there is no external field, the K and minus K spin are at the same amount and they are moved to the opposite direction. Hence, there will be no equivalent current. However, when there is a large external field, there will be an imbalance between the K and minus K space. In this case, there will be an equivalent charge current. Depending on whether the equivalent charge current is in the same direction with the current with flowing, then the second harmonic RXX can show a high resistance case and low resistance case. So with the conclusion, we can think that when the external field is parallel with the first harmonic spin, it's high resistance case. Then if the external field is anti-parallel to the first harmonic spin. It's a low resistance case. So here is showing the published data with bismuth selenide in XY scan. It can be seen that the second harmonic signal reaches the high resistance when the field rotates 90 degrees to the y-axis when the current is flowing along x-axis. It means that when current is for positive x current, the spin is aligned in the positive y direction. This is the same with the published bismuth selenide spin texture and also the positive spin Hall angle case. Then in this work, we performed the XY and ZY scan for the angular dependent field scan in tellurium medium tellurium fault. It can be seen that the first harmonic signal, the dark curve, shows a sign signal angular dependence with a period of 180 degrees, which is invariant under the reversal of the magnetic field, while the second harmonic shows a period of 360. Which reflects the spin direction. From the previous explanation, we can conclude that when the spin angular momentum is parallel to the external field direction, it will show high resistance case. When the spin angular momentum is anti-parallel to the external field, it will show low resistance case. So here is our scanning results. By combining the XY scan curve and the ZY scan curve, the red curve and the black curve, we can see that the XY curve indicates that when the current flow along plus X direction, the in-place spin align along Y, the supportive spin in case, then if it's for the ZY scan, its static deviation is from the 90 degree, which means that it has a small Z spin, which makes the Canting angle around 8 degrees. So, however, when the temperature decreases to 10 Kelvin, the Canting angle increases to 60 degrees. So nextly, we perform another experiment is that we rotate the sample with 180 degrees, but keeps the current flowing direction and magnetic field rotate direction is the same, which means that now we are flowing current from the A-axis to minus A-axis. In this case, it can be seen that the Z-spin Canting direction has been changed from plus 8 degrees to the minus 8 degrees. However, this angle is very small. It's only 8 degrees, which can also accidentally induced by error bar. So we performed the same experiment under 10 Kelvin, which shows a much larger Canting angle. By changing the current flowing direction from A-axis to minus A-axis, it can be clearly seen from the figure. Then the Canting angle has changed from the positive case to the negative case, which is 60 degree along A-axis and minus 60 degree along minus A-axis. This is similar to the published Nature Physics data, which shows Canting angle of 30 degree and minus 30 degree. Then for the double check, we do another experiment. In this case, we keep the sample direction the same, but changes the current flow direction. For example, firstly, we flow current from right to left side. Then now we are flowing current from the left to right side. In this case, from our conventional spin Hall effect and also either the spin Hall effect or the spin momentum locking, the Y spin should also change its sign, and the effect the new thing from our material is that when we change the current direction, the Z spin should also change its sign, and the result, the total spin direction should change 180 degrees. We can also read this from the figure. The high resistance case, the change shifted 180 degrees. This is consistent. The experiment result consistent with our theoretical prediction. Then If we try another case, if we flow the current in the high symmetry axis, which is also called B axis, it can be clearly seen that there is almost no deviation between XY scan, ZY scan, exactly along 90 degree, which means that the spin is aligned in the XY plane. And also, the same experiment has been done in another device, which shows the canting angle and A-axis, and but no Z spin along B-axis. Besides, by extracting the amplitude of second harmonic resistance, we can find that the amplitude is linearly dependent on both field and current. It's consistent with the published data. So in a summary, the three-dimensional spin texture has been observed in tandem-retaining form when current is flowing along A-axis, while no Z-spin can be observed when current is flowing along B-axis. And also the second harmonic resistance is linearly dependent on both current and the field. The canting angle can be estimated from this measurement. The published data is at for 20 nanometer bismuth cell line and 60 Kelvin. The canting angle can be 30 or minus 30 degrees dependent on the current direction. So in our experiment, for a 35 nanometer tandem 4 and room temperature, and A-axis is 8 degree and minus A-axis is minus 8 degree, while and along B-axis is 0 degree. So for a 22 nanometer device, it shows canting angle at the A-axis, but no Z-spin at the B-axis. Yeah, that's all. Thank you. I'm hoping for your suggestion and questions. Thank you very much.
Thank you. So now the floor is open for questions and comments. Yes, Hing, go ahead.
Hi, thanks for the interesting result. So I want to ask you, what's the difference between the first harmonic spin and second harmonic spin? And also, you also mentioned about the canting angle. Can you repeat again, what does the canting angle tell you about the spin?
You mean how does the canting angle mean the spin? Or
what does the canting angle represent? Like, for example, you have canting angle of like certain degree.
Okay. Yeah. Okay, sorry. I should explain this earlier. So, for example, this may be the XYZ axis. This is the XY. Then so when usually when current is flow along X direction, then there will be a spin along Y axis. This is a conventional spin Hall effect.
Yes.
However, in this material, the spin can slightly tilted to the Z direction. So then we call this angle as a canting angle.
Oh, okay.
Yeah.
All right, understood.
So yeah, somehow it can be seen as the strength of the Z spin compared to the Y spin.
All right, thank you.
Yeah, we have time for one more question if anybody wants to ask. No. Okay, so thank you, Yakun. So let's move on to the
last. Thank you very much.
Thanks a lot. Let's go to the last presentation. Avinash, you are ready?
Yeah. Now you can hear me.
Yeah, I can hear you, but it is little noisy. Can you speak again?
Hello.
Yeah, we can hear you. Go ahead.
Thank you. Good afternoon. My name is Avinash, and today I am going to present my work on active strain control of terahertz spin current. So there's basically terahertz spin current and the active control of using strain. So first I will discuss what is terahertz and how we can generate the terahertz spin current, and then finally I will discuss about my results using strain, how we can control. So as we know that terahertz is a bridge between the electrical and optical frequency in a electromagnetic spectrum. So this one has many advantages because the terahertz photon has energy in the region of like various elementary processes where we can have various resonance spectra, and it can help in understanding the material properties as well. So how we can generate the terahertz spin current pulses? So basically, in a typical spintronic emitter, what we do is we have a ferromagnet and heavy metal interface. When we sign the femtosecond pulse on this heavy metal ferromagnet interface, we can excite the ferromagnet, and due to this, there is ultra fast demagnetization and super diffusion of spins. So due to this, there is an injection of spin current from ferromagnet to heavy metal. So which leads to the basically inverse spin Hall effect in heavy metal, and we get the charge current. So charge current is basically defined as the JC is equal to gamma JS cross M by M, and whereas the gamma is the spin Hall angle of the material, and by changing the material like heavy metal, we can control the charge current, and also if we change the fluence, we can control it. And it also depends on the magnetization direction of the ferromagnet. So by these parameters, we can control based on this equation. So let me, so there is various ways to control actively this terahertz amplitude
participants,
because so when suppose by applying the magnetic field, we can control the terahertz amplitude as well as pulse, and also by increasing the pump fluence of the laser, we can control the terahertz amplitude. But we cannot control just by increasing the fluence, the phase of the terahertz. So by combining the photo and magnetic field effect, we can, there is a report like we can switch the phase of the terahertz pulse. So these are some active ways, and there is electrical way by using the current. But all these, like if we use the magnetic field, the device cannot be scalable at very small size. And also if we use the current, maybe there is too much leakage current in the system. So to avoid these, we propose a device where we use the artificial multi-ferrite structure. So our device looks like something this, where PM and PT is a ferroelectric and NIF is a ferromagnet, and PT has heavy metal layer. So in order to do the terahertz measurement, first we do the IV characteristic of device to find the switching voltages of the PM and PT layer. So these plus EC and minus EC basically the switching voltage at positive and negative sides. And now we use this switching voltages to basically apply see the sequence and then apply the electric field to see the effect of the voltage on the device. So first what we did the X-ray diffraction measurement by applying the electric field on the device. So what we see by applying the electric field, we can see the shift in the X-ray diffraction pattern. So this clearly shows that there is a strain in the device when we apply the electric field. So further, we calculated the strain using this spectra, and we found that by cyclic sweep of electric field, it is forming a butterfly loop. And now what we wanted to do by using this strain, which is basically due to the PM and PT layer, there is adjacent layer which is ferromagnet, how this strain will affect the magnetization of the ferromagnet. So we did the FMR spectrum measurement at different electric field, and then we find that this also forms a butterfly behavior. So this clearly indicates that we can directly correlate that the strain can calculate the control the effective magnetization of the ferromagnetic layer. So now, after confirming this, that strain can control the effective magnetization, we use this system to do the terahertz spin current measurement by applying a different voltages. So for that, we use the terahertz time domain spectroscopy measurement. So our device is here. So if I zoom it, it will look like this. So we assign the laser pulse and we apply the electric field across the thickness of the device. So what we do, if we suppose do the measurement by applying 8 kilovolt and initial at 0. So by applying 8, we can see the increase in the amplitude. So which clearly indicates that with the applied electric field, there is increase in the amplitude of the terahertz pulse. Now what we do cyclic sweep of the electric field and measure the terahertz amplitude. So it also forms a cyclic butterfly behavior, which is similar to the strain as well as effective magnetation of the ferromagnet. So to further go into deeper, like in the system, we rotate the sample and we found that the opposite behavior. I mean, when we apply the electric field, amplitude got decreased, as in this case. And in this case, the cyclic sweep of the electric field will give us to the opposite butterfly behavior. So now we have to find the origin why this is happening. So for that, what we did, we basically did the VSM measurement by rotating the sample. So this is the normalized remnant magnetization with basically the rotation of the sample. So we see by rotating, we can see the change in the remnant magnetization of ferromagnet. So from here, we can find the EG and hard axis of the material. So EG axis along this direction and hard axis along the. So what we do, we set the sample in this direction first, and then we apply the electric field. So at 0, the remnants was lower here. So we see the hard hysteresis loop in the system. But when we apply the electric field, we can see the increase in the resonance magnetization, which is directly correlated with the increase in the terahertz amplitude. But what we will do when we basically align the sample in the EG axis direction, by applying the electric field, our resonance decreases in comparison to the 0 kilovolt per centimeter, which is basically opposite behavior which we got by rotating the sample in the previous slide. So from here, we can say that it's EG axis rotation mechanism through which we are able to control the terahertz spin current by applying the electric field. So till now, I have discussed how to control the terahertz amplitude. Now I want to control the amplitude as well as phase. So to control the phase, basically using the strain, it's difficult to control. I mean, switching of the terahertz pulse. For that, we need a small magnetic field. So first of all, we did the hysteresis measurement. Similar to the MH hysteresis, terahertz hysteresis also forms like this kind of behavior, where basically we apply the magnetic field and we measure the terahertz amplitude. So as you see that when we apply the electric field, this hysteresis loop sinks. So that means if we choose this point and apply the electric field from 0 to 10, we can see the switching in the phase of the terahertz pulse at a given magnetic field. So in basically in conclusion, what we did that we are able to measure the strain by electric field and then effect of a strain on the effective magnetization. Then further, how this control of effective magnetization using a strain will affect the terahertz amplitude and phase, we measure that. So in conclusion, we demonstrate the active strain control of terahertz spin current pulse. Thank you.
Yeah, thank you, Avinash. Very nice talk. So now the floor is open for questions and comments. Okay, Avinash, I go first in that case.
Yes.
Okay. So you are saying that the strain at the interface between nickel iron and PMN and PT.
Yes.
That is affecting the terahertz amplitude. Okay. And then
so
you are
basically
in your sorry, let me finish, please. So in your initial introduction slides, you talk about spin pumping, right? Using the ferromagnetic resonance.
Yeah, so here we calculate the effective magnetization control of using electric field. Yeah.
Yeah. So now, okay, it's just a very what to say naive question because of my lack of understanding. I'm asking. So ferromagnetic resonance, it is in a nickel iron, right? The frequencies are in gigahertz range. Okay.
Yes.
Whereas you're talking about in terahertz range. The spin pumping is happening in gigahertz range. And why is it happening? Why is it affecting the terahertz pulses? That is my.
Yeah, so I may make sure that like to clear it. Basically, we are not controlling the terahertz pulse in ultra fast time scale. We are applying the electric field on the sample, and because of the electric field induced strain, and strain affects the effective magnetization. So due to the change in the effective magnetization of the ferromagnetic layer, we see the different amplitude of terahertz amplitude. Terahertz pulse basically.
Got it. It's not a kind of dynamic measurement then.
No, it's not in the same time scale.
Yeah. That's what I am. Okay, I was in a wrong conception. Yeah.
Okay. No.
Yeah. Otherwise, the coupling between gigahertz and terahertz is not quite, because with AFM antiferromagnetic materials, yes, it is. It may be possible.
Yeah, but it's still not that high. I think the terahertz or some 0.2, 0.5 terahertz.
You're right. Yeah.
Yeah. Thank you.
It's clear now. Thank you. So, any other questions from the audience?
Vinas, very nice talk. So I have one question just.
Please.
Have you tried any magnetic measurement by applying the electric field?
Yeah. So we one of the dynamic measurement that confirms that it is forming the butterfly behavior, and we do also do the VSM measurement here. I think. Yeah, this one.
So it's under an electric field, is it?
Yeah. So we apply the electric field at room temperature, and we see this butterfly, not butterfly, it's change in the eminence magnet. Basically, the loop becomes hard and easy because the squareness changes.
But I wonder, means in VSM, when you have contact, so how you apply the electric field there?
Oh, so for that, basically, we had the device. Maybe I can show from here. So we have this device. We deposit our main functional device is this NIFE, PT, and the PMNPT. It's a ferroelectric, and we deposit the copper at the bottom. Both side polished substrate we use. So we deposit the copper at bottom, not very thick because it should be a little bit transparent, and then we make a electrode from top and bottom, and then apply using the 2410 source meter that we have. We can apply around like higher voltages.
Okay, thank you.
That's a good question. Yeah. So any other questions we have? Yes, Shaprit, last question. Yeah.
Okay. Hi, Avinash. Because I don't know much about this, I think I also have missed out. You may have mentioned how you measured or quantified the strain in the nickel iron. Was there any structural properties or like how it was?
Okay. So first of all, we do not measure the strain on the NIFE. We measure the strain on the PMNPT. So this strain curve is basically for the ferroelectric layer, which is affecting the NIFE layer on top. But because NIFE is a polycrystalline on, I think, so it will not affect the. I mean, it will affect, but we are not measuring the strain on the NIFE layer. We are measuring the strain by applying the electric field on the PMNPT layer, which is basically the growth of NIFE on and PT on top adjacent to that. So it will transfer the strain from this layer to another layer.
Okay, so just a quick follow-up then. It can be considered as a passive strain getting from the ferroelectric layer. So is there also a possibility that the actual strain which is getting delivered might be slightly less or something like that, right?
Yes. It's always, It also depends on the thickness, and if you deposit some interface layer on that, it will, affect less. So that always be there, right?
Okay, thank you.
Yeah, thank you.
Yeah, thanks, Shaprit, and thank you, Avinash. Very
thank you.
Yeah, different from.
Can you stop sharing?
Yeah, please stop sharing.
Thank you.
So with this, I believe that we conclude this student presentation session, and we have 10 minutes break, and I request Dr. Varun to take over from there.
Okay. Yeah.
Okay. Thank you, Varun. Okay. So I see you guys. Yeah. Thank you very much.
Thank you very much, Dr. Chandra.
Yeah.
To take care for this.
So you please take over the next section. I will join a little later.
Okay. I'll take care. No problem.
I have a meeting to attend. Thank you so much.
Okay.
Bye.
Hello, Professor Akedi. Welcome.
Hello. Good morning.
Good morning. Yeah. So this is we have 10.
Good afternoon in Singapore.
Yeah. How are you doing?
Well, fine. Well, we have a few minutes now. I can try to.
Yeah, it's good. Yeah, you can check whether it's well sharing or not. You have 10-minute break.
Yeah. So I should count. Share the screen. Huh? So can you see my presentation?
Yes, everything is
okay.
perfect. Yeah.
Yeah, just to check. Okay. So I did vaccinated just a few hours ago.
Yeah, I'll let you know. Means you have 10 minutes.
Looks everything is okay. 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 So tomorrow you will continue, no?
Yeah. Yeah. Tomorrow also full day.
So if I will have a chance, probably I can look for some.
Yes. That will be really good.
Unfortunately, it's during the night, so now it's 9 and something.
Yeah, it's morning to you, right? Yeah, this is always a challenge when we have this online talks and overseas speakers. For example, our first plenary talk was by Professor Sarah Majetic. Oh, that for her it was around 9 p.m. there.
No, 9 p.m. is okay for me as well. But 2 p.m. or 3 p.m. is too late. Yeah. Yeah, just to have any watch for to check the time.
Yeah, we have 5-6 minutes to start. So I'll introduce and then you can start that time.
Okay.
So after 5 minutes, yeah. Yeah, so this should break some.
Yeah, I will take some water as well. Okay.
Yeah.
In fact, I would prefer always face-to-face meeting. Yeah, but
yes, hope
because if
soon
you're
it will
just
be
like
normal.
if your PC, if your computer, you don't have this feeling like
Exactly, definitely, it cannot be the same as we have
yeah, but
face to face.
this is what we have.
So you have 3 affiliation. So all in the same university, right? Different departments.
Yeah, this is the two different departments, but Gilbert is like foundation from local government. I have I have a visionary in chemistry faculty, but also we have laboratory in polytechnic school. So therefore, I placed 3 affiliations. So generally,
Okay.
So.
Very nice. Okay, I think now it's 4:30 and we can start. Welcome back. So this is a plenary talk given by Professor Joku, and he is from Department of Advanced Polymers and Materials, University of Bosco, Spain. He has several other affiliations as well. He did his PhD from his PhD is from Institute of Solid State Physics. There is a Russian Academy of Science, and he is currently a professor of Advanced Polymer and Materials of the Physics Materials University at Bosco. And he has 600 referred papers in international journals, citation more than 10,000, and he had published several books, chapters, and also associate editor of IEEE Magnetic Letters. He has several others distinguished awards. So I cannot name all here. So let's welcome Professor Arkady for an excited talk on soft magnetic microwires for technological applications. Welcome, Professor. Please start.
Hello, good morning or good afternoon. Thank you for giving me this opportunity to share our results. So we are from from Basque Country, from Spain. Most of my colleagues. And here you can see the outline of my talk. So after short introduction, I will speak on microwires as a suitable materials for different applications. So mostly we are dealing with amorphous microwires, but also with crystalline. So we can, I will speak about possibility to tune magnetic properties and the man-wall dynamics in these materials on giant magnetic impedance effect, and also a little bit on high frequency applications, so in smart composite materials. And then I will give you a few examples of applications. So in fact, you can see the pictures of San Sebastian. We are in the north of Spain, and almost in the frontier between Spain and France, in the Atlantic coast. Here you can see different images of our group, and even I want to say that Professor Fer now is belong to our group like distinguished professor. He discovered the magnetic resistance. So in fact, we doing with studies of magnetic wires. They are part of magnetic materials, soft magnetic materials, and magnetic materials generally can have different shapes, like ribbons shown here, and different exciting applications in different sectors, and after automobile space industries, and magnetic recording, etc. Well, magnetic wires are known since many years, and at the beginning they were crystalline, like around whiskers, Wigand wires, and with discovery of rapid quenching technique, amorphous wires started to be studied, and there are different families of amorphous materials produced by different techniques, like in rotating water is the most convenient one. Also melt extracting, and the last family of thinnest wires. In fact, we can produce in quite broad range of diameter, so-called glass-coated microwire. So we work in this family of microwires, and there are many very exciting applications of that materials. For example, you can see this is the web page of IHA Micro Intelligent Corporation. I copied it for this presentation. So one of the most exciting applications is in magnetic field sensors, which is suitable, for example, for cell phones, for cell phone technology. Also smartwatch, and in fact, I cannot see part of my screen by some reason, but maybe, yeah. And last but not least, that we also these materials could be suitable for smart composite materials with wiring illusions. And so these applications are based on giant magnetic impedance effect. Just to rightfully explain what is this. So this effect deals with change of impedance of magnetic conductor and the application of magnetic field. So in fact, this dependence on magnetic field is affected by magnetic anisotropy of materials. Therefore, magnetic properties of materials are quite important. And the origin of this dependence is the dependence of the skin penetration depth of, on magnetic permeability, given by this simple equation, simple expression. Low dimensions are quite important because in this case, the skin penetration depth should be below the dimensions of materials. Therefore, thin magnetic wires are important. And since the origin of this effect could be understood from this picture. So if you flow the current through your sample, now this is the cross section of your sample. The current is now flow through the whole of the sample. Then now if you increase the current frequency, now the penetration depth is shown here. So the skin effect is becoming relevant. And now if you apply magnetic field, you have change of penetration depth because of dependence of penetration depth on magnetic field through the magnetic permeability. Another promising application is related to the domain wall propagation. So in fact, it was considered among 10 most emerging technologies by MIT. And in this case, controllable domain wall propagation by either by current or by magnetic field could be used for this development of this restricted memory. Another application are related also with magnetic logics, and in all these cases, magnetic wires, thin magnetic wires are proposed. If you, this is just for education purpose. So, in fact, the magnetic domains have been reported more than 100 years ago. And what is important that on the application of magnetic field, the domain wall, the wall which separate different domains or different magnetization orientation can move for application of magnetic field. And in this case, in our case at least, we will deal with the so-called disposal regime when the domain wall usually is given by this dependence on magnetic field. So when the domain wall velocity versus magnetic field presented by this linear dependence, because above some magnetic field there is some kind of Volcker behavior, quite complex, and below there is important contribution of thermal activation. So the problems with domain application of domain wall or controllable domain wall propagation is the velocity of the domain wall and also a way to control the domain wall dynamics of materials. So my talk will be focused about these two main applications in a phenomena in microwires. So in our laboratory, we're working mostly with so-called glass-coated microwires, which could be produced by rapid emission from the melt. So if you can see the schematic picture of application facility. So now, first we prepare the metal ingot with the solid composition, then we melt it by inductor, and then draw first glass capillary, and then metal fuse this glass capillary, and then we can form this quite uniform magnetic microwires. Typically, dimensions are micrometers, the diameter of the microwire, and the length could be up to a few kilometers in the continuous microwire. And they have some different properties. For example, one of them is simple and fast fabrication process. Here, for example, you can see the most modern setup in our spin-off company, which is near San Sebastian. And of course, the most important for this talk for us is quite soft magnetic properties, which could be exhibited by these materials if they have amorphous structure. And these properties are magnetic bistability, which is closely related to the manual propagation. And also another properties, well, of course, soft magnetic properties and J magnetic impedance effect. And another one is thin dimensions. For example, for 1 gram of materials, we can produce up to 1 kilometer of continuous microwires. And also glass coating provide another functionality like biocompatibility and good corrosion resistance. So these are the advantages of our materials. And magnetic softness is usually related with the amorphous structure. So for amorphous, it means that the structure of our materials is liquid-like or glassy-like, if you like it. And then it could be realized in system. This is schematic picture, schematic sketch of the phase diagram. When you have deep eclectic, and then you can quench very fast from liquid state to solid state and fix a classic like state at room temperature. And this amorphous material do not have defects typical for crystalline materials like grain boundaries, dislocation, etc. So it's one of the main origin of magnetic softness of that kind of materials. Now we try to, in this slide, I will try to compare the dimensionality of different materials. So in monomorphous materials, there are mostly two families. One is the ribbons, which prepared by also by trapezoid by different kind of technique, wires, and of course very well-known influence preparation technique, which is in fact slower and more expensive. And usually cast materials like ribbons and wires present better magnetic softness by some reasons. We're dealing with microwires, which cross section is smaller than conventional ribbons or wires. And if you now compare the scale of ribbons, wires, and thin films, our materials are something between thin films and these more bulky materials. So this is one of the advantages of our materials, because we could be prepared with low dimensionality, but still with amorphous structure. In this talk, I will speak about different experimental techniques, like a method to measure hysteresis loop. In fact, this is conventional method, which employ just magnetizing of the sample by solenoid and picking up the signal by pickup coils. And also we measure the manual dynamics by 6-like experiments. So in this case, there are 2 pickup coils, but usually we use several. So in this case, once we integrate the manual travel along the mic, along the sample, and then we can pick up the signal and know the distance. We can calculate the manual velocity. Also, important technique which we realize in our laboratory, we can nucleate, inject them and roll in different part of microwires of our sample by local local magnetizing coil, and then we can measure so-called the manual so-called nucleation profile on our samples. And for giant magnetic impedance effect, we employ so-called Rockshell method with sample holder, which allows us to measure magnetic impedance effect with quite broad range of frequencies. So magnetic properties of our materials are affected very essentially by the composition. And this is because the composition affects the magnetostriction of the material. So the most common system is cobalt and iron-rich systems. And this system, this is the magnetization, and this is the magnetostriction. So it can change from positive and high to small and negative. And at some compositions, we can get even nearly zero magnetostrictive compositions. If the composition is with positive magnetostriction, we can have so-called bistable hysteresis loop. Bistable is because below some critical fields, we don't have even hysteresis loop, and then abruptly appear this square hysteresis loop. And the magnetization can turn positive or negative magnetization direction in two directions. And in this sense, our samples are magnetically very stable. And this is because once we apply the reversal magnetic field, there is fast domain wall propagation, and you can see in this picture. And then this is the origin of this perfectly squared hysteresis loop. So usually we follow this logic. So we first choose the composition which is going well for our properties, then choose the geometry, and then we can tune the properties of our materials by reversible processes, for example, local heating, mechanical stresses, thermal treatment, and in this way we can fit the properties of our materials to desired applications, and we can get optimal magnetic properties of our materials. So first I will focus on magnetic bistability. I already explained a little bit. So, and in fact, this effect is related closely to the mass structure of our material. This is the schematic picture of the mass structure of iron-rich microwires with positive magnetic friction. And this squared hysteresis loop is attributed to a single axial domain, which in fact the origin of the appearance of this domain is exchange energy, because in long and thin samples the magnetization is tended to be light in axial direction. And therefore, in fact, the important is the length of the sample because of the magnetizing field and these closure domains. And if the ratio between length and diameter is high enough, we can get this squared hysteresis loop, the real hysteresis loop. And so I already mentioned that we can inject a domain wall in any places. Therefore, if the applied field is high enough, this single domain wall propagation, which I mentioned before, could be affected by another domains. And here, for example, you can see the magnetization profile of one of such samples. So this single domain wall propagation appears between the switching field, which is correspond to this nucleation field at the end of the sample, and the minimum nucleation field in the middle part of the sample. And this is the range in where we can get this linear, almost linear dependence of the manual velocity on applied magnetic field. The origin of these fluctuations in the nucleation of profile of which I showed before, related with the defects. So now if we move our sample and nucleate domain wall in different places, we can, by this technique which I showed before, so we can get this picture similar to the previous slide. And this fluctuation is because of the when we nucleate domain wall in the middle of the sample and propagate it, the nucleation field is closely related to the magnetic anisotropy, which in turn is affected by magnetic elastic energy. So the origin of these fluctuations is related to the effect, for example, in homogeneity of glass, in homogeneity of internal stresses, etc. So now if we compare the domain wall dynamics, the dependence of the domain wall velocity magnetic field for one of the thinnest samples which we studied, about 2.8 micrometers with thin nanowires prepared by a sputtering technique. So we can see that in our case, the domain wall velocity is usually, even without any additional treatment, is about 1 order higher than in nanowires, for example, thermal nanowire. And the origin, so there are different viewpoints on the origin of such faster domain wall propagation. One, of course, is related to perfectly cylindrical shape of our samples. And this is, in fact, quite relevant for the application. Another one could be related with low demand wall damping, probably related to the amorphous structure of our sample, and also shielding from the surface, because one of the important origins of the peak of the demand wall is related to the surface roughness of the sample. Here I will show you the possibilities to tune the demand wall dynamic of our materials. So first, the important contribution, which is affect magnetic properties of amorphous materials, is magnetic elastic energy, and it depends on mostly on two parameters: magnetic restriction and internal stress. So if you speak about magnetic restrictions, be tuned by mostly by the composition. So these are iron nickel and iron cobalt systems. So it could be, so we are interested in positive magnetic restriction because of the relationship between hysteresis loop and the composition. And so we can tune the magnetic elastic energy, changing the chemical composition also. But also important are internal stresses. So because in our case, especially in our case, because we have simultaneous solidification of metallic nucleus surrounded by glass coating during the rapid quenching, shown in this picture. And the important issue is that the thermal expansion coefficients of glass and metal are different. Then if you cool very fastly together both materials, you can have shrinkage of both materials, but they shrink in different way. This picture are a little bit complex, but the most important, this is the dependence of internal stress on the radius of the microwire. So important is that these stresses are mostly of axial origin. So axial one are the highest one, and only in the interface between glass and metal they change the sign. And the strength of these internal stresses could be tuned by support flow ratio. So as thicker the glass, as more glass we have, volume of glass we have, as stronger these internal stresses for fixed diameter of our materials. In this way, we can tune the hysteresis slope of our materials by changing the ratio between linear diameter and total diameter of microwire, and then even magnetic properties. But I will show you also that the demand wall dynamics is also affected by these properties. So, for example, here we choose two different compositions of different magnetic restriction, and then the same row ratio. So we fix the geometry of the samples. Sorry, and then what we see that in both cases the velocity versus magnetic field present this linear dependence, but this slope is different, and the slope of this magnetic field dependence is given by this relationship, where S is the demand wall mobility. So demand wall mobility can be tuned by magnetic friction in this case, so by magnetic elastic energy. Then another case, we fix the composition, so we fix the magnetic restriction, but then we change the row ratio. And the highest row ratio means the smallest internal stress. And again, you can see that the slope is affected by magnetic elastic energy, which is in this case is related to the row ratio between diameter of inner of metallic nucleus to total diameter of microwire. And then another dependence is we just apply the stress during the demand wall propagation and see how it change the dependence. So as shown here, so increasing the stresses applied, in this case applied stresses for fixed composition, we have decrease of the slope or decrease of the demand wall mobility and the application of wide stresses. So it means that in the case of amorphous materials, the magnetic elastic energy is quite a relevant issue for tuning the demand wall dynamics for materials. And it could be understood because one of the origin of damping is related to the Gilbert damping parameter, which is affected by magnetic elastic energy. So this is one of the sources of damping in this material. So now if we choose the composition with low magnetic restriction, but still with positive magnetic restriction, we can get quite high nominal velocities, in this case up to 2.5 kilometers per second. So it's very fast, and in fact very close to sound velocity in magnetic materials. And this is one of the possibilities. However, there is another possibility. For example, this is composition with quite high magnetic restriction. And what we did, we applied the annealing of the sample. So in this case, the hysteresis loop is affected very little. But so you can see from this picture, you can increase drastically also the diamond wall dynamics, velocity. So even from starting from very short annealing from 4 minutes, the diamond wall velocity increase a lot. So these are some possibilities to tune the diamond wall dynamics in these materials. In this case, you can see the diamond wall mobility change with the time of annealing. In this way, increasing quite high, about 7 square meters per ampere volume. These materials. Another application of these materials of magnetically bistable behavior is magnetic tags, as shown here. So in this case, you can use different samples with different positivities, and the hysteresis loop of the array of these microwires represented like different steps. And in this case, our proposal was to just increase linearly the applied magnetic field, and at different times we have these sharp voltage peaks, which correspond to a remanipulation of different samples in the tag. And then we can digitalize these magnetic codes and to get this coding system, which allow to use these materials, for example, for coding, like labels in supermarkets, etc. So this is another possibility for application. Now I will turn a little bit on magnetic impedance effect, on possibility to tune the magnetic impedance of these materials. Again, the magnetic restriction is quite relevant. And what is important in this case that materials with squared hysteresis loop present low magnetic permeability, low magnetic field, and therefore usually the giant magnetic impedance effect in these materials is quite low as compared to cobalt-rich materials. And the highest magnetic impedance effect is observed in cobalt-rich materials with nearly zero magnetic restriction coefficient, like shown here. So in the case of just cobalt-rich materials without iron, when the magnetic restriction is negative and little bit large, and the magnetic anisotropic field is quite large, and also the giant magnetic impedance effect is low. This is these are the main possibilities. However, magnetic properties of amorphous materials could be tuned by different factors. For example, the listed in the classical paper from Muller. And here are the factors which we paid attention in our studies. For example, one of the factors I already mentioned is the internal stresses, which could be tuned by ratio between diameter of metallic nucleus to total diameter. Here we have a fixed decomposition with nearly zero magnetic restriction. And as shown from this picture, all these materials are quite soft, so with positivity about 4 ampere per meter, so 20 times less than the terrestrial magnetic field. But the magnetic anisotropic field can be tuned by the geometry, by the internal stresses. And this, you can see from this picture that the magnetic anisotropic field could be defined roughly like this point of deportation is in fact a function of rho ratio or internal stresses. And for example, if we now measure magnetic impedance effect in this system, we can get the smallest volume of internal stresses and the highest volume of magnetic impedance ratio to the materials with the smallest magnetic elastic energy, smallest internal stresses. So from this picture, it looks like the stress relaxation should be important. However, it's not so simple in these systems. I will show you just a couple of examples. So just annealing of cobalt-rich materials results in fact in growth of relatively high growth of persitivity is shown here. This is dependence of time of annealing, but the same occurs with annealing temperature. And in fact, just relaxation of stresses, many cases even results in decrease of magnetic impedance effect. And so to understand this picture, these results, we should take into account different factors. One is the dependence of magnetic restriction on internal on stress. So this is in fact one of the old papers showing dependence of magnetic restriction on applied stresses, but internal stresses could be also relevant. So we assume that in our case occurs the same. So when we release part of internal stresses by annealing, so we can get magnetic restriction from negative to positive, and then the magnetic permeability can be decreased by this change of the magnetic restriction. And in fact, we confirmed this part. And so special care should be considered for this post-processing of these materials. So here are different examples with different materials, and of course, still these materials present magnetic impedance effect, but it's lower than in as prepared sample. However, these materials present also annealing-induced magnetic stability, and therefore these kind of materials could be also interesting because they can present both interesting properties like the manual propagation shown here and also GME magnetic impedance effect. However, sometimes our purpose is to improve the magnetic impedance effect, and one of the possibilities is to use the so-called induced magnetic anisotropy for our samples. Here are some examples. So we try to anneal our samples on the stress, and so here you can for example see dependence of history slope on stress annealing. So this is the as prepared samples. After annealing, our history slope becoming more and more rectangular. However, if you apply stress annealing under certain conditions, we can decrease the coercitivity, and even in some conditions, we can even improve the magnetic softness shown in this picture. So in this case, the annealing temperature should be high enough, and the applied stress also should be high enough. So this is for comparison is presented the history slope of annealed at the same temperature sample, and the blue one is the stress annealing sample. So this is one of the way to to improve the magnetic softness of our one. And if we now fix on behavioral magnetic impedance effect, we can see that the stress annealing can pass the magnetic impedance ratio. So here is the dependence of magnetic impedance ratio on applied magnetic field. For example, probably the most illustrative part is picture that showing that the giant magnetic impedance effect will be improved, drastically improved at some frequency range by stress annealing. Another way to tune the magnetic properties is use of Joule heating. In this case, the relevant feature of Joule heating is that a part of the heating of the sample will also apply this circumferential magnetic field, which allows to improve the magnetic anisotropy of our samples, so also improve the magnetic softness and giant magnetic impedance effect, as shown in this picture. Also, we observed this increase of the maximum giant magnetic impedance ratio in some frequency range on the application of the power sample. In this case, we were able to achieve magnetic impedance ratio up to 650%, quite large values, much larger than, for example, magnetic resistance effects. So what was interesting that in fact cobalt belonged to critical materials, and for application which involve a lot of microwires, we try to improve magnetic softness to even iron-rich material. Sorry. So we try to use the same philosophy, and then we found that even in rich materials we can induce transversal anisotropy by stress annealing, shown in this picture. And then magnetic impedance effect would be also improved, as shown again here. So this is as prepared sample where the magnetic impedance effect was quite low, and after stress annealing, we were able to improve magnetic impedance effect. So systematic studies show that we can induce, we can tune the hysteresis loop of our materials, changing, for example, fixed stresses hysteresis loop, as shown here, from almost rectangular to almost inclined. Also, and also we can improve, of course, the magnetic impedance because of this transverse anisotropy which we induced by this annealing. And here are absolute value of impedance, even of the diagonal components of impedance. And what is important that this stress-induced anisotropy depends also not only on annealing temperature but also on applied stresses, and it's not totally reversible. So part of this induced anisotropy is appears even after annealing out of our samples. So hysteresis loop is quite stable. And so what is important that such stress-induced anisotropy depends on temperature, on applied stress, only partially reversible, and therefore quite promising even for optimization of the magnetic impedance effect in rich materials. This dependence on annealing conditions induced us to propose interesting method to tune the properties of these materials, like annealing at variable temperature. So in this case, we can get microwires where the hysteresis loop can change from place to place. For example, we place our materials in the furnace where the temperature was changing with distance where the microwires have been placed. And the hysteresis loops in this case varied from almost rectangular to almost inclined, depending on the temperature distribution inside of the furnace. And what could be the application of this threaded magnetic anisotropy? Here we can see the demand hysteresis loop and demand wall propagation in as prepared material. So we have this rectangular hysteresis loop. Then we measured the demand wall dynamics in different places of microwires. So 1, 3, 1, 2, and 3 means that we employed several pickup coils, number 1, number 3, number 2, and the demand wall velocity was almost the same in the whole materials. And this reflected by peaks on the pickup coils. So they have these peaks, and the sequence correspond to the demand wall propagation, shown here from coil 1, point 2, 2, point 3. And now what happened? We have applied stress and locally feed our sample at some point. In this case, we can induce magnetic anisotropy locally in this place, and we can create so-called defect or softer magnetic properties in this place. In this case, the demand wall dynamic change from this regular one to this irregular one means we now can nucleate demand wall even in the place we locally fit it under stress our samples, and we can change the demand wall dynamics now. So then demand wall nucleate in even in the middle of the sample, and then demand wall propagation could be this way could be controlled by some way. Quite recently, just this year, or even this paper is not published yet, so we will try to see what happened with the demand wall propagation in these materials applied by stress annealing at temperature gradient. So in this case, we can get different hysteresis loop along the samples, and the gate of the inner core in which demand wall propagates can be tuned, and it could be reduced in the part of the sample. And here are interesting phenomena. For example, in as prepared state, where we have homogeneous inner axial demand, the demand wall velocities were the same in the whole of the sample. But now, if we measure the domain wall propagation in the place where we have different dimensions and different anisotropy, the domain wall velocity is not the same in different places of materials. In this case, we also can control the domain wall propagation of these materials by this graded magnetic anisotropy induced by stress and limited variable. In fact, if we speak about origin of induced anisotropy in these materials, there are several different possibilities. One is related to the stress-induced anisotropy coming from higher ordering, for example, cobalt and iron. So on the application of magnetic field or stress, these pairs of cobalt iron can be orientated, and this give the origin of this appearance of magnetic field or stress induced anisotropy in this material. However, for example, for the case of iron-rich materials, this is not the case because in this case we have only one ferromagnetic element. In this case, so-called structural anisotropy related with some angular distribution of atomic bonds or small anisotropic structural rearrangement is considered for origin of this anisotropy. So I see I have about 10 minutes, even a little bit less. I'm going a little bit to the part of the application. So after finishing this part of the tuning the magnetic impedance effect and even the manual dynamics. So what is important for for us that we can observe magnetic impedance effect even at gigahertz frequency. You can see pictures even until 3 gigahertz. We have a large change of impedance and application of external field. And this gives us opportunity to design the concept of tunable composite materials with ferromagnetic materials. In this case, if we have magnetic impedance at high frequency, it would give us opportunity to non-contact, non-destructive monitoring and without any contacts using just antenna. And this induced us the possibility to use composite materials with wire inclusions. And in this case, the magnetic properties and magnetic impedance effect of these wire inclusions can give rise to stress or temperature dependence of absorption or reflection of these composite materials on the application of electromagnetic waves. In this case, we use this anechoic chamber in our laboratory and use just one antenna, and we are measuring the composite materials with wire inclusions. Theoretically, the dispersion of the permittivity in these two kinds of materials with long wire inclusions and short wire inclusions should be different. So in short wire inclusions, we can observe from theoretical point of view kind of resonances which correspond to the length of the wire inclusions. In the case of long wire inclusions, we have this kind of plasmonic-like behavior with real imaginary part. And so we prepare different composite materials. And here we can see some experimental results. First, of course, it is important that the reflection or transmission parameters are affected by magnetic field in both cases, in the case of long wire inclusions and short wire inclusions. So it means we can realize this dependence of high frequency properties like reflection transmission on magnetic field. And here was one of the last results, also published just a couple of years ago. We tried to use the same concept for control of the polymerization process. So we introduced our wire inclusion during the polymerization and see how it changed for example, the transmission. And what we observed that during the solidification, there is a change of internal stresses, and hence we can observe this change of transmission in these composite materials during the solidification. Then we can also monitor the process of fabrication of such composite materials. And the applications could be quite different, for example, starting from human body to self-monitoring of construction, etc. So in this case, you can use so-called smart bricks or smart inclusions in some constructions, and then we can control by transceiver, by antenna from time to time. So another applications are related with, of course, with magnetic impedance chips, or in fact, Aisha Steels were involved in the preparation of MI chips. In this case, the size was about 0.5 millimeter, and the heart of this chip is the magnetic microwires placed here, and so it was proposed for using in quite sensitive MI elements for cell phones. And the principle is that you have 3 pieces of microwires placed orthogonally, and then we can measure the magnetic impedance in 3 dimensions. You can get the vector of magnetization in your MI chip. And there were different papers comparing properties of different magnetic field sensors. So my sensors are quite good. So the only problem was the size. And recently, because of the thinner wires developed, for example, by us, the size could be drastically decreased in this case. And this gives us a possibility to measure a very small magnetic field because of magnetic impedance magnetic impedance isn't quite high field sensitivity, even to biomagnetic field. So here I just want to provide some paper of group from Japan, from group of Professor Mori and Uchiyama, that they were able to detect blood and even brain activity using magnetic impedance technology. And in fact, this sensitivity is quite high and even comparable with SQUID technology, but the technology is much cheaper than SQUID technology, of course. So now group will also develop different sensors, for example, temperature sensor and magnetic elastic sensor. For example, in the case of temperature sensor, the magnetic impedance above the temperature disappears. And in this case, we can somehow relate measurements of magnetic impedance with temperature. In this case, we apply the stress, and you can see how it changed the magnetic impedance. And this is kind of calibration proof. And if we fix the magnetic field at some point, we can change the affect the AC voltage from pickup coil and measure this dependence on applied stress.
Maybe you may conclude in a minute or two so that we can have questions. Yeah.
And probably the last and not least, also even last year, we, in collaboration with the Japanese group, they developed MI sensors based on the ASIC technology in the integrated circuit technology. Here are some examples and paper published by Magnet Design. So in fact, this is the last transparency. And in summary, I want to say that magnetic microwaves can present different exciting properties. For example, fast angle propagation, which could be manipulated through the magnetic elastic anisotropy, and the appropriate post-processing is quite important. And the high magnetic impedance effect is suitable for different applications like magnetic field detection, stress, temperature monitoring, and quite good properties could be obtained. And in fact, thank you. And if you're interested, you can contact me or look in these books, the appropriate information. Last and not least, we have 2 special issues in NDP journals, processes, and sensors. If you're interested, you can contact me to submit.
Yeah, thank you.
So thank you.
Thank you very much, Prof. Kadi, for a nice presentation. So now we have open for questions. So please raise your hand and then I'll ask to unmute. Yeah, let me go first. So I have a question. Means how you control this thickness of these micro wires? I mean, the thickness of the metal and the glass outside.
In fact, during the fabrication, we have kind of antenna which measure the impedance during the fabrication. And there is a relationship between the signal, well, proportional to the electrical resistance. And then we can monitor this parameter during the preparation, and then we can. So during the preparation, we have different parameters. Like, for example, we have receiving bobbin, receiving spool, which can rotate in different velocity. And also, the glass is also supplying by very slow velocity. So with supplying of glass, we can control the thickness of glass coating, and with rotating velocity, we can control also the diameter of metallic nucleus. And we can monitor it and save in the computer, and then choose the piece which we are interested in.
Okay, very nice. And another question is, so you use the pre-alloyed material in starting. Am I right? The material, starting materials.
Yeah, we use generally transition metals, iron, nickel, and cobalt. There are some restrictions because of chemical reaction between glass and the rare earth materials. However, for example, recently we were working on phosphate alloys, memory alloys, and also magnetocaloric. I didn't mention it because this is a little bit a part of this topic, but we're doing also the part of research. And also another kind of materials which we use is kind of granular materials. For example, we use cobalt copper materials, and these materials we can they are crystalline, but we can tune the magnetic resistance.
So melting copper kind of materials is also no problem for this induction melting.
In fact, copper? Initially was so 3D materials, iron, nickel, cobalt, and all these materials with metalloids. So in fact, for amorphous materials, we need kind of metalloids in order to decrease the melting temperature. So if you are not interested in amorphous materials, we can do still iron, cobalt, and nickel rich alloys. And with phosphate alloys, for example, nickel manganese gallium, we can work over nickel manganese indium, manganese indium. But in the case of use of manganese, it's evaporated during the process. So we need to be careful with concentration of manganese. So sometimes we need to choose the materials. And always we have to choose the materials which have no chemical reaction with the glass. Usually we use Pyrex type glass or Durand type glass, but we can also choose different kind of glass.
Yeah. Thank you. Any questions from audience? Okay. Yeah, I think so. Yes, Sabri, please go ahead.
Hi, Prof. I have this, I think, a very basic question which I might have missed actually. So in your iron cobalt wires, which are kind of amorphous in nature, so when you can you comment on how the output would vary instead of using this amorphous iron cobalt, and if you use crystalline iron cobalt, the magnetostriction constant would be higher for such microwires, right? And for the application, why do you prefer the amorphous?
Okay, thank you. Well, good question. In fact, the main, also one of the main point is that amorphous materials present better ductility, much better ductility. So in this case, you can do with your wires what you want. You can apply stresses. In the case of crystalline materials, usually they are much more fragile. For example, we have this problem with phosphate alloys or even cobalt copper, so because even to make electrical contact, they are much fragile to be destroyed or break quite easily. And another point is that the magnetic softness is affected by amorphous structure. So if you have, we measure sometimes in also magnetic impedance affecting crystalline materials, but usually amorphous materials present much better magnetic softness. I don't know if I answered your question, so but this is main point for us. Oh, but in any case, I didn't show you, but in the case of iron-based materials, we can get so-called nanocrystalline materials. The problem is again the magnetic properties. For electrical contacts, for example, for magnetic fields measurements, we should pay much more attention to electrical contacts. But they sometimes present comparable magnetic properties and also good magnetic fields. For example, fine metal materials. But this is they are not iron cobalt rich materials. Usually, iron cobalt rich crystalline materials present higher magnetic anisotropy, and therefore they are relatively magnetically dark.
Okay, yeah, it helped. Okay, thank you.
Thank you.
Varun, we cannot hear you.
Hello.
Yeah, okay. We can hear, yes. Oh, again, we cannot hear you. No.
In fact, I remember I was visiting Singapore about maybe 10 years ago in Nursing National University of Singapore. They had such kind of facility also to study this kind of materials at that time.
Okay, thank you. Probably Varun wants to close the session. He speaks, but we cannot listen. So let's thank Professor Akadi and end the session. Thank you very much. Thank you all. Bye-bye.
Thank you. Okay. Have a good luck. Okay.